What if everything we thought we knew about ancient technology was incomplete? Picture for a moment a world where our ancestors didn't just track time with simple sundials or crude water clocks, but built devices of such astonishing complexity and precision that they rival the accuracy of modern atomic timekeeping. These weren't just tools for marking hours, they were sophisticated instruments that predicted celestial events, coordinated agricultural cycles, and even modeled the movements of planets with breathtaking accuracy. For centuries, these engineering marvels lay hidden in forgotten ruins, buried beneath jungle canopies, desert sands, or ocean depths, their secrets waiting to be rediscovered by curious minds willing to challenge conventional historical narratives. Today, we're embarking on an extraordinary journey to explore 25 of these remarkable timekeeping devices that fundamentally reshape our understanding of what ancient civilizations were capable of achieving. From the intricate bronze gears of a 2,000-year-old astronomical calculator found in a Mediterranean shipwreck to precisely aligned stone observatories in the Americas that capture solstice sunlight with millimeter accuracy, these discoveries tell a story of human ingenuity that spans continents and cultures. We'll venture into lost cities where ancient astronomers carved entire calendars into mountainsides, examine water clocks that measured time with hydraulic precision we still struggle to replicate, and decode mathematical systems that tracked celestial cycles across centuries without error. This exploration isn't just about admiring ancient technology, it's about confronting the profound questions these devices raise about the development of human knowledge. How did cultures separated by oceans and millennia arrive at such similar, sophisticated understandings of time? What knowledge was lost during the Dark Ages that these artifacts are only now helping us recover? And what might these discoveries teach us about our own relationship with time and technology today? As we uncover these secrets together, prepare to have your perspective on human history permanently transformed. The journey begins now, and what we're about to discover might just change everything you thought you knew about our ancient past. To truly appreciate these astonishing devices we're about to explore, we need to step back and understand the world that created them, a world without standardized hours, without global time zones, and without any of the modern conveniences we take for granted. Ancient civilizations weren't just casually noting the passage of days, they were engaged in a profound intellectual endeavor to comprehend time itself. Their survival, prosperity, and spiritual beliefs depended on this understanding. Farmers needed to know precisely when to plant and harvest crops to avoid starvation. Religious leaders required exact timing for ceremonies aligned with celestial events. Navigators depended on astronomical knowledge to traverse vast oceans and deserts. This practical necessity became the mother of incredible invention across multiple continents simultaneously. What's truly fascinating is how different cultures, completely isolated from one another, arrived at similar sophisticated solutions. The Egyptians along the Nile, the Maya in the dense rainforests of Mesoamerica, the Babylonians between the Tigris and Euphrates rivers, the Chinese along the Yellow River Valley, all developed complex timekeeping systems that reflected their unique environments and cultural needs, yet shared fundamental principles of astronomy and mathematics. The Egyptians created water clocks that measured nighttime hours independently of the seasons, while the Maya developed calendar systems that could accurately track Venus cycles across centuries. These parallel developments suggest something fundamental about human consciousness. Our species seems hardwired to seek patterns in nature and to quantify our experience of time's passage. These ancient timekeepers weren't just practical tools, they represented the highest scientific achievements of their eras. The construction of a precise water clock required understanding hydraulic principles and fluid dynamics. Creating an accurate sundial demanded advanced knowledge of geometry and astronomy. Developing calendar systems involved sophisticated mathematics, including in some cases the concept of zero, which wouldn't appear in Europe for centuries. The engineers and astronomers who designed these devices were the equivalent of today's NASA scientists and Silicon Valley engineers, pushing the boundaries of what was technologically possible within their cultural and material constraints. They worked with stone, bronze, water, and shadow rather than silicon and electricity, but the intellectual sophistication was remarkably similar. The cultural significance of these timekeeping devices cannot be overstated. In many ancient societies, time was not seen as a simple linear progression, but as a sacred cycle connecting humanity to the cosmos. The Mayan calendar, for instance, wasn't just a way to count days, but a complex system that interconnected religious ceremonies, agricultural cycles, and cosmic events into a unified whole. Egyptian obelisks functioned as giant sundials that literally cast the pharaoh's divine connection to the sun god Ra across temple courtyards. Stonehenge's massive stones captured solstice sunlight in ways that must have seemed like magic to those who witnessed it. These devices served as physical manifestations of a culture's understanding of its place in the universe, both practical tools and profound philosophical statements. This historical context makes the discoveries we'll explore even more remarkable. When we find a 2,000-year-old device that could predict lunar eclipses or track planetary movements with gear systems of astonishing complexity, we're not just looking at an interesting artifact, we're glimpsing into the mind of an ancient engineer who solved problems of precision measurement with nothing but mechanical intuition and careful observation. We're seeing the culmination of centuries of accumulated knowledge, much of which was later lost and is only now being rediscovered. These creations represent humanity's first steps toward scientific thinking, our earliest attempts to bring mathematical order to our experience of the cosmos, and in many ways they establish the foundation upon which all modern timekeeping technology is built. The quest to uncover these ancient technological marvels reads like something from an adventure novel, with explorers and scholars following faint clues across the globe. They've pursued leads from crumbling manuscripts that mention strange devices, deciphered star charts that point to forgotten observatories, and listened carefully to indigenous oral histories that preserved knowledge of these sites long after they were abandoned. Often, the most significant breakthroughs happen completely by accident. A farmer plowing a field unearths a strange stone carving, construction crews building a new road slice through an ancient foundation, or drought-receding waters reveal structures hidden for centuries. These chance discoveries remind us that our planet's surface is merely a thin veil over a deeply layered history, with incredible artifacts waiting just beneath our feet. The environments that have protected these timekeeping devices are as varied as they are challenging. Dense jungle vines have swallowed entire cities, their humid embrace actually preserving stone structures by protecting them from temperature fluctuations and erosion. Desert sands have buried mechanisms in dry, sterile conditions, preventing corrosion and decay that would have destroyed them elsewhere. Submerged shipwrecks have kept bronze gears safe in cold, dark waters, their anaerobic environments preventing oxidation that would have turned them to dust on land. While these conditions have preserved these marvels, they've also made discovery incredibly difficult, requiring specialized skills and technology to locate and carefully extract these artifacts without causing damage. Modern technology has completely transformed this field of exploration. Where early archaeologists might have relied on intuition and manual excavation, today's researchers use satellite imagery that can detect subtle variations in vegetation growth that signal buried structures. Ground-penetrating radar allows teams to map what lies beneath the surface without ever breaking ground, creating three-dimensional models of hidden chambers and mechanisms. Laser scanning technology can capture every detail of a site with millimeter accuracy, preserving digital records that can be studied indefinitely. These non-invasive methods mean that fragile artifacts can be analyzed in situ, their original context preserved while still revealing their secrets through virtual examination. Each discovery represents more than just an individual artifact. It's a crucial piece in the vast puzzle of human technological development. When researchers unearthed the Antikythera Mechanism from that Mediterranean shipwreck, they weren't just finding a curious bronze object. They were recovering evidence that ancient Greek technology was far more advanced than previously believed. The identification of precise astronomical alignments at Mayan sites didn't just confirm their calendar systems, it demonstrated a sophisticated understanding of celestial mechanics that rivaled contemporary European knowledge. Every fragment of pottery with astronomical markings, every stone structure with solstice alignments, every gear recovered from an archaeological site adds another day to point to our understanding of how ancient civilizations perceived and measured time. This ongoing search continues to reshape our historical narrative, revealing that many cultures developed precision timekeeping independently, each bringing their unique perspective to this fundamental human endeavor. The work is painstaking, often requiring years of study to understand how a single device functioned, but each discovery brings us closer to appreciating the full scope of our ancestors' intellectual achievements. What drives this relentless pursuit is the growing realization that we've underestimated ancient technological capabilities for centuries, and that many more marvels likely remain hidden, waiting for the right combination of traditional knowledge and modern technology to bring them back into the light of understanding. Imagine a sponge diver emerging from the blue depths of the Mediterranean in 1901, clutching not treasure but a lump of corroded bronze and wood he fished from a 2,000-year-old shipwreck near the island of Antikythera. Initially dismissed as a piece of nautical debris, this unassuming lump would sit in a museum storage room for decades before someone noticed the faint traces of precisely machined gear teeth. This was the first glimpse of a device so advanced, so conceptually brilliant, that its discovery would force us to completely rewrite the history of technology. We now know this object as the Antikythera Mechanism, and it stands as a shocking anomaly in the archaeological record, a masterpiece of engineering that should not have existed for another 1,000 years. What makes this device so revolutionary is its breathtaking mechanical complexity. Using advanced X-ray and imaging technology, scientists have been able to peer inside the encrusted fragments and digitally reconstruct its inner workings. They found not just a few simple gears, but an intricate clockwork universe of at least 30 precisely interlocking bronze gears, all housed within a wooden case no larger than a shoebox. This wasn't a simple calendar, it was a portable, hand-cranked planetarium. By turning a handle on the side, an ancient user could advance the mechanism to any date and see the positions of the sun, moon, and likely the 5 known planets moving across a dial representing the zodiac. It could predict solar and lunar eclipses with remarkable accuracy, not just telling you when they would happen, but the color and direction of the eclipse, information crucial for the omens and superstitions of the time. The sheer genius of its engineering is perhaps best illustrated by its solution to a particularly tricky astronomical problem: the moon's irregular orbit. We know now that the moon doesn't move at a constant speed around the Earth. It speeds up and slows down in its elliptical path, The ancient Greeks observed this anomaly, and the maker of this device engineered a brilliant mechanical solution. They used a pin and slot mechanism connecting two gears, a large gear representing the moon's average motion and a smaller one accounting for its irregularity. As the gears turned, the pin would slide back and forth within the slot, subtly speeding up and slowing down the rotation of the indicator hand to perfectly mirror the moon's actual, wobbling path through the sky. This level of sophisticated mechanical modeling is simply staggering for its era, but the mechanism's purpose extended beyond pure astronomy into the very fabric of Greek society. One of its dials was dedicated to tracking the 4-year cycle of the Panhellenic Games, the ancient precursor to our Olympics. This wasn't just a sporting event, it was a sacred period of truce and celebration that unified the Greek world. The ability to accurately predict the timing of these games, alongside celestial events, highlights how this device sat at the intersection of science, religion, and culture. It was a tool that could tell you when to expect the next eclipse, when the games would be held in Corinth, and what phase the moon would be in on any given day, a unified theory of time packaged in bronze. The inscriptions covering its surfaces, once thought to be simple labels, have been revealed as a detailed user's manual, explaining the complex outputs and the philosophical concepts behind them. This was not a one-off toy for a wealthy patron. It was a sophisticated instrument, likely based on a tradition of astronomical knowledge and mechanical craftsmanship that has been completely lost to history. The fact that nothing approaching its complexity appears again until the astronomical clocks of medieval Europe forces us to confront an uncomfortable truth. We have vastly underestimated the technological capabilities of the ancient world, and the Antikythera Mechanism is our most powerful piece of evidence that our timeline of invention is profoundly flawed. This one device, rescued from the seafloor, shatters the linear narrative of progress and hints at a golden age of science that flickered brightly before being swallowed by the dark. While the Greeks were engineering intricate bronze gear systems to model the heavens, an entirely separate civilization on the other side of the world was achieving similarly breathtaking precision through monumental stone architecture. Deep within the jungles of the Yucatan Peninsula, the Maya constructed observatories of such sophisticated design that they could track planetary cycles across centuries with nothing but carefully aligned windows and doorways. The most famous of these, El Caracol at Chichen Itza, stands as a testament to their astronomical genius, a circular tower perched on rectangular platforms, its name meaning the snail for the spiral staircase within, but functioning as a powerful celestial observatory. What makes El Caracol and similar structures so remarkable is their precise alignment with specific astronomical events. The building's windows and doorways weren't simply placed for architectural symmetry. They were carefully positioned to frame Venus at its most extreme northerly and southerly positions on the horizon. During these precise moments, the morning star would appear perfectly centered within these stone apertures, signaling to Maya priests important periods for warfare and royal ceremonies, as Venus was closely associated with the god Kukulkan and believed to influence human affairs. Other alignments captured the setting sun at the summer and winter solstices, while additional apertures tracked the movements of other celestial bodies with similar precision, creating a comprehensive astronomical tracking system in stone. The mathematical foundation behind these observations was arguably as advanced as the architecture itself. The Maya developed a vigesimal number system, base 20, that included the concept of 0 centuries before it appeared in European mathematics, allowing them to perform complex calculations and work with enormous numbers. Their long count calendar could track time over periods spanning thousands of years with remarkable accuracy, while their Venus calculations were precise to within 1 day in 500 years. This mathematical sophistication enabled them to predict celestial events with reliability that would have seemed magical to contemporaneous European societies, all achieved through careful observation and computation without mechanical aids. These observatories served dual purposes that modern science often separates. They were simultaneously precise scientific instruments and sacred ceremonial spaces. During equinoxes, the play of light and shadow on nearby structures like the Temple of Kukulkan would create the illusion of a serpent descending the pyramid steps, connecting astronomical events to religious mythology in visually dramatic fashion. Priests could use these precisely timed phenomena to demonstrate their connection to the cosmic order, reinforcing their spiritual authority while simultaneously gathering the astronomical data needed to maintain their complex calendar systems. This integration of science and spirituality represents a holistic world view that modern society has largely lost. The practical applications of this astronomical knowledge extended far beyond temple ceremonies into the very survival of Maya civilization. Their ability to accurately predict seasonal changes informed agricultural practices, telling farmers exactly when to plant and harvest crops in a challenging tropical environment where timing was crucial. Eclipse predictions likely helped maintain social order during events that were often viewed as omens of disaster, allowing priests to prepare the population ritually and psychologically. The Venus cycle, which they calculated at 584 days, extremely close to the actual 583.92 days, governed the timing of military campaigns and royal successions, embedding celestial patterns into the very fabric of political power. What's particularly astonishing about Maya astronomical achievements is that they were accomplished without optical instruments like telescopes. Their observations relied entirely on the naked eye, using artificial horizon markers, sight lines along buildings, and notches in distant structures to track celestial movements with extraordinary precision. They developed correction systems similar to our leap year concept to keep their calendars aligned with astronomical reality, demonstrating a sophisticated understanding of the slight discrepancies between calendar time and actual celestial motion. This level of naked eye astronomy represents a peak of human observational skill that has rarely been matched in history. The legacy of these observatories challenges our modern assumptions about technological progress. While we might consider gear-based mechanisms like the Antikythera device as more technologically advanced, the Maya achieved similar results through architectural genius and mathematical sophistication, creating observatories that required no moving parts yet maintained their accuracy for centuries. Their stone structures have outlasted many mechanical devices, continuing to mark celestial events accurately to this day, a testament to the durability of their design. This suggests that there are multiple paths to technological achievement, and that our conventional timelines of scientific progress may need to account for different cultural approaches to solving the same fundamental problems of understanding and measuring our universe. Meanwhile, along the fertile banks of the Nile, Egyptian engineers were mastering the flow of water itself to create timekeeping devices of remarkable sophistication. Their clepsydras, or water clocks, represented a monumental leap from simply observing shadows to actively controlling a natural element to measure time's passage. The earliest versions were beautifully simple yet effective. A stone or ceramic vessel with a small hole near the base would be filled with water, and the time elapsed was measured by how much water had drained out, marked by lines inside the container. But the Egyptians quickly realized that as the water level dropped, the water pressure decreased, slowing the flow and making the clock less accurate over time. Their ingenious solution was to redesign the entire system, creating inflow clocks where water dripped into a container at a constant rate, allowing the rising water level to indicate the passing hours on a calibrated scale. This shift from outflow to inflow principles demonstrated a profound understanding of hydraulic physics that wouldn't be formally documented for centuries. The true genius of these devices emerged in their most advanced forms, which compensated for the changing length of nighttime hours throughout the year. Unlike our modern equal-length hours, the Egyptians divided both day and night into 12 segments each, meaning the length of an hour actually changed with the seasons. Some clepsydras featured multiple sets of hour marks or adjustable scales that could be modified throughout the year to maintain accuracy. The most sophisticated versions used a complex system of multiple chambers and overflow mechanisms that maintained a constant water pressure, ensuring the flow rate remained steady regardless of how much water was in the reservoir. This hydraulic regulation system was so effective that it maintained timing consistency to within minutes over a full night's measurement, a precision that would challenge even early mechanical clocks millennia later. In temple settings, these water clocks evolved into elaborate ceremonial instruments that blended timekeeping with cosmic symbolism. The Karnak water clock, one of the most magnificent examples discovered, features exquisite carvings of celestial deities and star charts that connected the flow of time to the movement of the heavens. As water flowed through these sacred timekeepers, priests could conduct nighttime rituals with precise timing, ensuring offerings and prayers occurred at astronomically significant moments. The clocks weren't merely functional objects but served as physical manifestations of the Egyptian belief in the cyclical nature of time and the cosmic order they called Mat. The gentle, continuous flow of water mirrored the eternal flow of the Nile itself, connecting the measurement of hours to the very lifeblood of their civilization. What's particularly fascinating about these devices is how they spread across Egyptian society, adapting to different needs and scales. Simple household clepsydras helped regulate daily activities and market hours, while massive temple versions governed the complex schedule of religious ceremonies. Some evidence suggests they were used in legal contexts to ensure fair speaking times in courts, giving us our modern concept of time running out for legal proceedings. The portability of smaller water clocks made them invaluable for nighttime military operations and travel, allowing Egyptians to maintain temporal order even when sundials were useless. This widespread adoption shows how thoroughly the precision measurement of time had become integrated into both practical daily life and the spiritual framework of one of history's most remarkable civilizations. While the Egyptians perfected water flow and the Maya aligned stone with stars, medieval Chinese engineers were constructing what might be considered the most sophisticated mechanical device the world had ever seen. In the 11th century, during the Song dynasty, a brilliant polymath named Su Song designed and built a clock tower that would remain unequaled in complexity for centuries. This colossal structure soared over 30 feet into the air, not merely telling time but functioning as a complete astronomical observatory and public spectacle that merged mechanical genius with cosmological understanding. At its heart was a revolutionary invention, the first known escapement mechanism, a device that would later become the fundamental component of all mechanical clocks, though Europeans wouldn't develop their own versions for another 200 years. This ingenious component regulated the power from a constant water flow, transforming erratic energy into measured, precise motion that drove the entire complex machine with remarkable consistency. The clock's most breathtaking feature was its rotating armillary sphere, an intricate bronze model of the celestial sphere positioned on the tower's top level. This instrument didn't simply represent the heavens, it actively tracked, and displayed the real-time movements of stars and planets with astonishing accuracy. Through a series of precisely calculated gears driven by the water wheel escapement, the sphere completed one full rotation every 24 hours, mirroring the apparent motion of the night sky. Astronomers could use this mechanical universe to predict planetary conjunctions, map unfamiliar stars, and verify celestial events with a reliability previously unimaginable. The device even accounted for the uneven motion of the sun through the zodiac, a sophisticated astronomical concept that required advanced mathematical understanding and mechanical implementation. Below this celestial model, the clock tower came alive with automated figures that transformed timekeeping into public theater. At each quarter hour, beautifully crafted wooden mannequins would emerge from behind doors to strike bells, sound drums, or present tablets announcing the time. This auditory and visual display made the sophisticated timekeeping accessible to everyone in the capital city of Kaifeng, not just the educated elite. The automation extended to a series of rotating figures that displayed special time announcements for dawn, dusk, and other significant periods, creating a continuous performance that connected the community to the cosmic rhythms governing their lives. This integration of practical time measurement with public spectacle represents a holistic approach to technology that served both scientific and social functions. The power behind this mechanical marvel was a water-driven mechanism of extraordinary sophistication. Unlike simple water clocks that measured time by flow, Su Song's system used a constant level tank that maintained steady water pressure to ensure uniform operation regardless of how much water was in the main reservoir. This water turned a massive vertical wheel that drove the entire mechanism through a complex series of gears and shafts. The true brilliance lay in the escapement that controlled this wheel, allowing it to rotate in precise increments rather than continuous motion. This tick-tock action, so familiar in later mechanical clocks, was born from water power rather than weights or springs, demonstrating an alternative path of technological development that achieved similar precision through different engineering principles. What makes this clock tower particularly significant is its documented influence on later timekeeping technology. Detailed technical drawings and descriptions survived in Su Song's book, which found its way along trade routes to Europe. While no complete European mechanical clocks appear until the 13th century, the conceptual similarities suggest knowledge of Chinese horological principles may have traveled westward, accelerating European clockmaking development. The clock's legacy extended beyond timekeeping too. Its precise astronomical measurements allowed Chinese scholars to create star catalogues and planetary tables of unprecedented accuracy, contributing to navigational advances and calendrical reforms that stabilized agricultural planning across the empire. This single structure represented the pinnacle of mechanical engineering, astronomical science, and public timekeeping, a triumph of human ingenuity that would not be surpassed in scale or complexity until the great cathedral clocks of medieval Europe, and even then, it took centuries to match what Su Song had achieved during what we often mistakenly call the Dark Ages. Meanwhile, in the arid landscapes of ancient Persia, engineers confronted a different kind of timekeeping challenge, one dictated not by the stars, but by the critical need to fairly distribute a precious and limited resource, water. Their solution was a marvel of both civil engineering and social organization, integrating sophisticated timing technology directly into the life-sustaining infrastructure of their communities. The Qanat systems they developed were far more than simple irrigation channels. They were vast, carefully engineered underground networks that tapped into aquifer sources at the foothills of mountains and transported water across deserts through gently sloping tunnels, sometimes stretching for dozens of miles. These remarkable structures brought life to otherwise uninhabitable regions, but their true brilliance emerged in the timing mechanisms that governed water distribution at the village level, transforming simple flow into measured, allocated time. At the heart of this system were water clocks specifically designed for resource management rather than mere timekeeping. These weren't the ornamental clepsydras of temples or courts, but robust, practical instruments built for daily agricultural use. The most common design involved large ceramic jars with precisely calibrated holes near their base, placed in larger containers of water. As water seeped into the jar, it would eventually sink, and the time it took to fill, a period known as a pani, became the standard unit for water allocation. Farmers would receive water rights measured in these time units, with local water masters using these devices to ensure equitable distribution according to complex scheduling systems that accounted for land size, crop type, and seasonal variations. The consistency of these ceramic timers was remarkable, maintaining accuracy through careful craftsmanship that accounted for water viscosity changes due to temperature fluctuations. The engineering sophistication extended to more complex regulator mechanisms that maintained constant flow rates despite varying water pressures in the Kanat system. Some installations featured floating indicators connected to valve systems that would automatically adjust openings to maintain consistent flow, acting as primitive but effective pressure regulators. Other designs used multiple outlet pipes of different diameters that could be opened or closed in combination to create precisely calibrated flow rates for different allocation periods. These mechanical solutions demonstrate an intuitive understanding of fluid dynamics principles that wouldn't be formally described in scientific terms for centuries, yet were being practically applied to solve real-world problems in ancient Persian communities. What makes these systems particularly fascinating is how they embedded time measurement into the social and economic fabric of agricultural communities. The water timer wasn't just a technological device, it was the physical embodiment of a social contract that ensured fair access to resources for all community members. The position of water master, the person responsible for operating the timers and maintaining the schedule, was often one of the most respected roles in the village, requiring both technical knowledge of the timing mechanisms and the trust of the community. This integration of technology with social governance represents an early example of how time measurement tools can shape and support complex human organizations, creating systems of fairness and order in challenging environmental conditions. The durability and precision of these timing methods allowed Persian agriculture to flourish in regions where water scarcity would otherwise have made sustained farming impossible. By precisely measuring and allocating irrigation time, communities could maximize crop yields while preventing the overuse that leads to soil salinization and resource depletion. Environmental management, concerns that remain critically important in arid regions today. The systems were scalable too, from small village installations with simple ceramic timers to major regional kanats that supplied entire cities and incorporated multiple timing stations along their distribution networks. This scalability demonstrates how the technology evolved to meet different community needs while maintaining the same fundamental principles of measured, equitable distribution. Perhaps most impressively, these ancient timing systems established patterns of water management that persist in modified forms even today in some regions. The underlying concept of time-based water allocation remains fundamental to irrigation management worldwide, and modern water distribution systems still grapple with the same essential challenges of measurement, fairness, and conservation that Persian engineers addressed millennia ago. Their solutions, emerging from practical necessity rather than abstract scientific inquiry, created sustainable agricultural systems that supported civilizations for centuries in some of the world's most challenging environments, proving that the most profound technological innovations often emerge from the basic human need to manage resources wisely and ensure community survival through precise measurement and fair distribution of time itself. While the Persians were mastering water distribution timing in their arid landscapes, ancient Greek engineers in Athens were creating a structure that would become one of the most sophisticated public timekeeping installations of the classical world. The Tower of the Winds, standing proudly in the Roman Agora, represented a revolutionary approach to time measurement by combining multiple technologies into a single elegant structure. This magnificent octagonal marble tower, built around 150 years before the Common Era, wasn't just a building. It was a complete meteorological and horological station that served Athens as both a scientific instrument and a public utility, bringing precise timekeeping to the heart of civic life in ways previously unimaginable. What made this structure truly extraordinary was its ingenious dual-function design that captured both time and weather patterns simultaneously. Each of the 8 sides faced a different cardinal and intercardinal direction, corresponding to the 8 wind deities depicted in beautiful sculpted reliefs along the frieze. These weren't merely decorative elements. Each figure actually functioned as the gnomon for a sundial carved into the marble surface beneath it. As the sun moved across the sky throughout the day, different sundials would become active, ensuring that from sunrise to sunset, at least one dial would always be accurately tracking the time. The precision of these sundials was remarkable, with carefully calculated hour lines that accounted for seasonal variations in the sun's path, allowing Athenians to read the time with accuracy to within fractions of an hour simply by observing which shadow fell where. The tower's true innovation, however, lay hidden within its walls, a sophisticated water clock that could maintain accurate time regardless of weather conditions or nighttime darkness. While the exterior sundials ruled the day, the interior mechanism took over when clouds obscured the sun or when darkness fell. This clepsydra used a constant flow system that maintained steady water pressure through multiple chambers and overflow mechanisms, driving a floating indicator that moved around a circular dial to show the hours. The water source was likely fed from the Acropolis above, providing consistent pressure that ensured reliable operation day after day. This integration of solar and hydraulic timekeeping created a 24-hour public time service that would have been invaluable for regulating market hours, court proceedings, and civic ceremonies in ancient Athens. The meteorological function of the tower added another layer of sophistication to this remarkable structure. Atop the roof stood a bronze statue of Triton holding a rod that functioned as a weather vane, indicating wind direction to sailors, farmers, and merchants who needed this information for their daily activities. The positioning of the tower on high ground made it visible from throughout much of the city, while the 8 wind deities on the sides corresponded to the directions shown by the weather vane above. This created a complete public weather station where citizens could simultaneously check the time, wind direction, and likely other atmospheric conditions that were important for maritime trade, agriculture, and daily life in ancient Athens. The architectural precision of the Tower of the Winds reveals the advanced mathematical and astronomical knowledge of its designers. The orientation of the building wasn't arbitrary. Each face was carefully aligned to maximize sundial accuracy throughout the year, with the northeast and northwest faces receiving optimal sunlight during summer months, while the southeast and southwest faces caught the lower winter sun. The marble construction wasn't just for grandeur either. The light-colored stone provided excellent contrast for reading shadow positions, while the material's thermal stability ensured the sundials wouldn't expand or contract significantly with temperature changes, maintaining their calibration across seasons. Even the interior water clock likely benefited from the stable temperatures within the thick marble walls, reducing evaporation and thermal effects on water viscosity that could affect timing accuracy. This integration of multiple timekeeping technologies represents a conceptual leap that wouldn't be matched for centuries. The Greeks understood that no single method could provide reliable timekeeping in all conditions, so they created a system where sundials, water clocks, and even astronomical observations, through the building's possible use as a sighting device, worked in complementary fashion. During sunny days, the sundials provided the primary time reference while simultaneously calibrating the water clock against the most reliable time standard available, the sun itself. At night or during bad weather, the water clock took over, maintaining continuity until the sun reappeared and could reset any accumulated error. This redundancy and cross-calibration approach shows a sophisticated understanding of error correction and system reliability that feels remarkably modern in its conception. The social impact of such a public timekeeping installation cannot be overstated. In a society where most people estimated time by the sun's position or crude water clocks, the Tower of the Winds provided a level of temporal precision previously available only to astronomers or wealthy individuals who could afford personal timekeeping devices. It democratized accurate time measurement, allowing merchants to coordinate transactions, citizens to appear in court at appointed hours, and the entire city to operate on a more synchronized schedule. This temporal coordination likely facilitated more complex economic activities and social organization, representing an important step toward the regimented time consciousness that would eventually characterize modern societies. The tower stood as both a practical tool and a symbol of Athenian technological achievement, demonstrating how the measurement and mastery of time represented a form of cultural and scientific sophistication that distinguished advanced civilizations from their neighbors. High in the Andes Mountains, the Inca civilization mastered the art of stone itself to create astronomical instruments that were both profoundly spiritual and incredibly precise. The Intihuatana stones represent perhaps the most elegant fusion of cosmic observation and religious devotion we've encountered yet. These weren't merely functional devices but sacred objects that literally connected Earth to the heavens in the Inca worldview. The name itself, Intihuatana, translates beautifully as hitching post of the sun, suggesting the Inca believed they could literally tether the sun to the earth at critical moments in its annual journey. This poetic concept was realized through astonishingly precise stonework that transformed solid rock into sophisticated celestial tracking instruments. At Machu Picchu, the most famous Intihuatana demonstrates this precision with breathtaking clarity. The central stone pillar rises from a carved bedrock base with angles and facets that correspond exactly to significant solar positions throughout the year. During the equinoxes, something remarkable happens. The stone casts no shadow at all at solar noon, standing in perfect balance with the sun directly overhead. This shadowless moment would have been a powerful symbol of cosmic harmony for Inca priests. On solstice days, the shadows fall along carefully carved grooves and alignments that point toward specific mountains on the horizon that held religious significance. The stone doesn't just measure time, it creates a physical dialogue between the built environment, the natural landscape, and the celestial sphere. What makes these structures particularly impressive is how they were tailored to their specific locations throughout the vast Inca Empire. While they shared the same basic function, each Intihuatana was uniquely designed for its latitude and altitude, accounting for the specific solar angles and horizon features of its location. The stone at Machu Picchu works perfectly at its elevation of nearly 8,000 feet, but would lose accuracy if moved even a short distance. This suggests the Inca developed sophisticated mathematical methods for calculating solar geometry and translating these calculations into stone with incredible precision. The craftsmanship itself is marvelously precise. The angles are sharp, the surfaces smooth, and the alignments accurate to within fractions of a degree, all achieved with stone tools rather than metal implements. The dual purpose of these stones reveals much about Inca society's integrated worldview. Practically, they served as agricultural calendars that told farmers exactly when to plant, when to harvest, and when the rainy season would begin. The precise tracking of solstices allowed communities to prepare for seasonal changes that meant life or death in the challenging Andean environment. Simultaneously, these were deeply sacred objects where priests conducted ceremonies aligned with solar events. During the winter solstice, when the sun reached its weakest point, ceremonies at the Intihuatana were believed to help hitch the sun and prevent it from disappearing entirely, ensuring its return and the renewal of life. This blending of practical necessity and spiritual practice shows how the Inca saw no separation between the material and cosmic worlds. The construction methods themselves remain somewhat mysterious, adding to the intrigue of these remarkable devices. The Inca worked with hard granite and diorite stones using only stone hammers, bronze tools, and sand abrasion, yet achieved finishes and precision that would challenge modern stonemasons even with power tools. The perfect right angles, precise planar surfaces, and careful orientations suggest they developed sophisticated surveying and astronomical observation techniques that have been largely lost to history. The resilience of these stones is equally impressive. They've endured centuries of weather, earthquakes, and even attempted destruction by Spanish conquistadors who recognized their religious significance and tried to dismantle them, though many survived through their massive construction and remote locations. The psychological impact of these devices on Inca society cannot be overstated. In a civilization without written records, the Intihuatana served as permanent, reliable markers of cosmic order that everyone could observe and understand. The dramatic light effects during solstices and equinoxes would have reinforced the power of both the religious and political structures that controlled these observations. When the sun's shadow perfectly hit a specific marker, or when the stone stood shadowless at noon, it demonstrated the priests' claimed connection to the divine and their ability to predict and even influence cosmic events. This gave the calendar keepers enormous authority while providing the entire society with a sense of order and predictability in a world that often seemed governed by unpredictable natural forces. Perhaps most remarkably, these stone calendars continue to function with undiminished accuracy centuries after their creators vanished. The Intihuatana at Machu Picchu still marks the equinoxes and solstices with the same precision it did when Inca priests conducted ceremonies around it. This endurance speaks to the sophistication of the original design. These weren't devices that required recalibration or maintenance, but permanent fixtures aligned with celestial patterns that themselves remain constant over centuries. The stones stand as silent witnesses to a civilization that looked at the same sun we see today and found a way to literally carve its movements into the landscape, creating a dialogue between human culture and cosmic patterns that continues to speak to us across the centuries. While the Inca were carving celestial alignments into mountain stone on the fertile plains between the Tigris and Euphrates rivers, Babylonian scholars were pursuing timekeeping through an entirely different medium, clay. Their astronomical diaries represent perhaps the most comprehensive and sustained scientific observation project in the ancient world, spanning more than 6 centuries of meticulous nightly recordings. Imagine teams of temple scribes positioned on ziggurat platforms, carefully noting the positions of planets, the brightness of stars, and the timing of lunar events on damp clay tablets that would then be baked into permanent records. This wasn't occasional stargazing, it was systematic data collection on an industrial scale, creating a celestial database of unprecedented depth and duration that would become the foundation of Western astronomy. The true genius of these Babylonian records lies in their mathematical sophistication, enabled by their unique sexagesimal number system, the same base 60 system that gives us our 60-minute hours and 360-degree circles today. This numerical framework allowed them to perform calculations of astonishing complexity, tracking planetary movements through elaborate arithmetical schemes that could predict lunar eclipses to within hours, even accounting for the subtle variations in the moon's orbit that make precise eclipse prediction so challenging. Their methods involved recognizing patterns in the vast datasets they had accumulated, identifying cycles within cycles that enabled them to model celestial motions with mathematical precision rather than mere geometrical approximation. They developed the zigzag function, a mathematical tool that could model the varying speed of celestial bodies, and systems of interpolation that filled gaps between observations with calculated values of remarkable accuracy. What's particularly astonishing about their eclipse predictions is how they achieved this without any geometrical model of the solar system. Unlike the Greeks, who would later imagine celestial spheres and epicycles, the Babylonians used pure arithmetic complex sequences of calculations based on the patterns they had detected in their centuries of data. They recognized the Saros cycle, a period of approximately 18 years after which eclipses repeat in similar patterns, but they refined this basic cycle with correction factors that accounted for its imperfections. Their lunar theories could predict the exact time of first visibility of the new crescent moon, a critically important religious and calendrical event, with methods so reliable that they remained unsurpassed until the Renaissance, more than 1,000 years later. The scope of these diaries extended far beyond mere planetary positions. Babylonian astronomers recorded weather phenomena, commodity prices, river levels, and significant political events alongside their astronomical observations, creating an integrated record of what they perceived as interconnected systems. A planetary conjunction might be noted alongside the price of barley and the level of the Euphrates, reflecting their world view where celestial and earthly events were intimately connected. This holistic approach, while different from modern scientific methodology, demonstrates their sophisticated understanding that multiple factors might influence their world, and that keeping comprehensive records could reveal patterns invisible to casual observation. The practical applications of this astronomical knowledge permeated Babylonian society at every level. Their precise calendar, regulated by astronomical observations, determined the timing of religious festivals, agricultural activities, and legal contracts. The ability to predict eclipses and other celestial events gave temple priests enormous social and political power, allowing them to demonstrate what appeared to be supernatural foresight. Kings would consult astronomical omens before making important military or political decisions, and the regular appearance of Venus as the morning or evening star marked significant periods in their ritual calendar. This integration of precise timekeeping with daily life created a society deeply attuned to celestial rhythms, where the measurement of time was not an abstract exercise but a vital component of cultural and religious practice. The preservation of this knowledge across generations speaks to the remarkable institutional stability of Babylonian scholarly tradition. For century after century, through conquests and changes of dynasty, the temple scribes continued their observations, maintaining consistent methods and terminology that allowed each generation to build upon the work of their predecessors. This continuity created a scientific tradition unique in the ancient world, where observations from the reign of Nebuchadnezzar could still be consulted and utilized by scholars working under Persian and later Greek rule. The clay tablets themselves, baked to durability, became a permanent library of celestial knowledge that could be referenced and analyzed across generations. Perhaps most impressively, the Babylonian astronomical tradition represents the birth of the scientific method in its most fundamental form: careful observation, systematic recording, pattern recognition, and predictive modeling. Their approach was essentially empirical, based on what they could actually observe rather than philosophical speculation about how the heavens ought to work. This methodology would eventually pass to the Greeks, who combined it with their geometrical approach to create the synthesis that would become Western astronomy. The fact that we can still read these clay tablets today and follow the calculations of ancient Babylonian astronomers with admiration for their precision and sophistication stands as powerful testament to humanity's enduring quest to understand and measure the cosmos through the careful, patient accumulation of knowledge across generations. While the Babylonians were compiling their celestial diaries on clay tablets and the Incas were carving solar alignments into mountain stone, on the Indian subcontinent a different kind of astronomical revolution was taking shape, one built on an epic scale of stone and ambition. The Jantar observatories represent perhaps the most dramatic and visually stunning approach to precision timekeeping ever conceived. Imagine approaching a complex where the astronomical instruments aren't delicate brass devices held in the hand, but monumental structures of stone and marble that tower over visitors, their colossal scales evoking a sense of both scientific grandeur and spiritual awe. Built in the early 18th century by Maharaja Sawai Jai Singh Roman II, these observatories weren't merely scientific facilities but physical manifestations of a ruler's commitment to understanding cosmic order through precise measurement. The centerpiece of the Jaipur complex, the Samrat Yantra, deserves particular attention for its breathtaking simplicity and precision. This isn't just a sundial, it's the world's largest sundial, standing as tall as a modern 9-story building, yet functioning with accuracy that would challenge many mechanical timepieces. The genius of its design lies in its equinoctial orientation. The triangular gnomon points precisely toward the North Pole, while the quadrants on either side are aligned with the plane of the Earth's equator. This orientation means that as the sun moves across the sky, the shadow cast by the gnomon moves at an almost perfectly uniform rate along the calibrated marble scales, allowing time to be read with astonishing precision. The shadow moves at approximately 1 millimeter per second, a pace that trained observers could use to determine time to within seconds, a level of accuracy that seems almost impossible for a device with no moving parts. What makes this precision even more remarkable are the subtle refinements built into the instrument's design. The scales aren't simple linear markings but incorporate corrections for atmospheric refraction, the bending of sunlight as it passes through the Earth's atmosphere that would otherwise introduce small but significant errors in measurement. The edges of the gnomon are beveled to create a sharp shadow line even when the sun isn't at its brightest, and the massive scale of the instrument itself helps average out small imperfections that would affect smaller sundials. The marble construction provides thermal stability, preventing expansion and contraction that would alter the calibration with temperature changes. Every aspect of the design reflects deep understanding of both astronomical principles and practical engineering considerations. Beyond the magnificent sundial, the Jantar complexes contain dozens of other instruments, each designed for specific astronomical functions. The Jai Prakash Yantra consists of 2 hemispherical bowls sunk into the ground, their surfaces carved with coordinate systems that allow an observer standing inside to precisely measure the altitude and azimuth of celestial bodies. The Ram Yantra features 2 complementary circular buildings with radial pillars that create a coordinate grid when viewed from the center, enabling precise angular measurements of stars and planets. The Digamsa Yantra is a simple but effective pillar surrounded by a circular wall that accurately determines the azimuth of celestial objects at the moment of their rising and setting. Each instrument represents a different approach to solving the fundamental problems of positional astronomy using nothing but stone, geometry, and careful observation. The mathematical sophistication underlying these instruments reflects centuries of Indian astronomical development. Indian mathematicians had developed sophisticated trigonometric functions centuries before they appeared in Europe, along with advanced calculus-like techniques for dealing with infinite series and variable motion. The construction of these instruments required understanding of spherical trigonometry to calculate the precise angles and orientations needed for accurate celestial measurement. The scales engraved on the marble surfaces incorporate complex mathematical functions that translate shadow positions or sight lines directly into usable astronomical data, effectively building the mathematics into the physical structure of the instruments themselves. This integration of advanced mathematics with physical engineering represents a unique approach to solving astronomical problems that differs significantly from both the mechanical complexity of European clocks and the arithmetic approach of the Babylonians. The social and cultural context of these observatories reveals their multifaceted purpose. While they were undoubtedly scientific instruments of the highest order, they also served important administrative and religious functions. Precise timekeeping was essential for determining the auspicious moments for royal ceremonies, religious rituals, and important state decisions according to Hindu astrological traditions. The ability to accurately predict eclipses and planetary movements reinforced the ruler's connection to cosmic order and demonstrated his command of the knowledge necessary to maintain social and spiritual harmony. At the same time, the observatories served practical purposes for calendar regulation, navigation, and timekeeping for the broader population, with the large instruments allowing multiple observers to simultaneously make measurements and learn astronomical principles. The construction techniques employed in building these massive instruments demonstrate remarkable engineering prowess. The stone used wasn't just piled up. Each block was carefully cut and fitted using traditional Indian masonry techniques that created stable structures capable of maintaining their precise alignments across centuries. The instruments were built using local materials and craftsmen, yet achieved tolerances that would be impressive even with modern construction methods. The fact that these instruments remain functional and accurate today, 3 centuries after their construction, testifies to the skill of their builders and the soundness of their engineering principles. They've survived earthquakes, monsoons, and the ravages of time while maintaining their astronomical precision, making them among the most durable scientific instruments ever created. Perhaps most impressively, the Jantar Mantar observatories represent a living tradition of astronomical knowledge that continues to this day. Unlike many ancient instruments that became obsolete and were abandoned, these stone observatories remain functional and are still used by local astronomers and students to make measurements and understand celestial mechanics. The large scales actually make them excellent educational tools. The principles of astronomy become visible and tangible when demonstrated on such an enormous scale. This continuity of use represents a unique bridge between ancient astronomical traditions and modern scientific practice, demonstrating that advanced knowledge can be preserved and utilized across generations when embodied in such permanent and well-designed forms. While Indian astronomers were building their monumental stone observatories and Babylonian scribes were compiling clay tablet records, Islamic scholars during the Golden Age were perfecting an instrument that would become the ultimate portable computer of the medieval world, the astrolabe. This wasn't merely a tool for telling time, but an elaborate mathematical instrument that compressed the entire known cosmos into an elegant brass disc that could be held in one's hand. The sophistication of these devices represents a pinnacle of scientific instrumentation that wouldn't be surpassed until the Renaissance, blending advanced mathematics, precise metalworking, and deep astronomical knowledge into objects of both practical utility and breathtaking beauty. What made the Islamic Astrolabe particularly remarkable was its multi-layered design that could be customized for different latitudes and purposes. At its heart was the mater, the main body that held a series of interchangeable plates called tympans, each engraved with coordinate grids specific to particular latitudes. Above these rotated the rete, an intricate openwork map of the most important stars that functioned like a star chart rotating over the coordinate grid. The entire assembly was topped with a rule and alidade sighting instruments that allowed users to measure the altitude of stars or the sun. This modular design meant a single astrolabe could be used from North Africa to Central Asia simply by changing the tympan plates, making it the most versatile scientific instrument of its era. The mathematical complexity embedded in these brass discs was extraordinary. Craftsmen had to precisely calculate and engrave stereographic projections, a mathematical technique that maps a sphere onto a flat surface for each latitude plate. This required solving complex trigonometric problems to ensure that the curved paths of stars across the celestial sphere would be represented as perfectly circular arcs on the flat tympan. The scales around the edges incorporated multiple calendrical systems, allowing conversion between Islamic, Persian, and Julian dates while accounting for the different lengths of months and leap year variations. Some advanced models even included mechanical computers with geared mechanisms that could model the irregular motions of planets or predict eclipse timings with remarkable accuracy. For timekeeping, the astrolabe offered solutions that were both ingenious and practical. By measuring the sun's altitude during the day or a known star's position at night, users could determine the time with precision that varied by only minutes from modern clocks. The instrument's capabilities extended to determining the 5 daily prayer times, a critically important function in Islamic society that required knowing the exact position of the sun relative to the horizon. Special scales helped calculate when dawn, noon, afternoon, sunset, and nightfall prayers should occur, accounting for seasonal changes in day length that made these times shift throughout the year. This religious application drove much of the innovation in timekeeping precision, as prayer times needed to be determined with consistency across the vast Islamic world. The manufacturing process itself represented a triumph of medieval technology and craftsmanship. Artisans employed lost wax casting techniques to create the intricate rete patterns, then used precision engraving tools to add the fine scales and markings that made the instruments functional. The precision required was astonishing. The scales on some surviving examples are accurate to within fractions of a millimeter, achieved entirely through hand craftsmanship without magnification. The brass used in their construction was carefully alloyed to resist corrosion while maintaining the rigidity needed for precise measurements. Many astrolabes became works of art as well as scientific instruments, decorated with elaborate engravings, Quranic inscriptions, and poetic verses that reflected their status as objects of both learning and beauty. The educational value of these instruments cannot be overstated. Learning to use an astrolabe required understanding fundamental astronomical concepts, mathematical principles, and geographical knowledge. Students would learn about the celestial sphere, the ecliptic path of the sun, the changing positions of stars throughout the year, and the relationship between time and the Earth's rotation. The astrolabe made these abstract concepts tangible and manipulatable, serving as a physical model of the cosmos that helped train generations of astronomers, navigators, and timekeepers. This hands-on approach to astronomical education contributed significantly to the preservation and advancement of scientific knowledge during a period when much of Europe was experiencing technological stagnation. The impact of these Islamic innovations extended far beyond the Muslim world through trade routes and cultural exchanges. Astrolabes reached Europe through Spain and Sicily, where they sparked renewed interest in astronomy and navigation. European craftsmen began producing their own versions, often copying Islamic designs and sometimes including Arabic numerals and inscriptions they didn't understand but recognized as markers of sophistication and accuracy. The mathematical principles embedded in these instruments, particularly the trigonometric methods used in their construction, would eventually influence European mathematics and astronomy, helping to lay the groundwork for the scientific revolution that would emerge centuries later. The astrolabe became a bridge between Islamic and European scientific traditions, carrying advanced knowledge from one civilization to another. Perhaps most impressively, these devices represented a holistic approach to knowledge that integrated science, art, religion, and practical daily life. A single astrolabe could help determine prayer times, navigate across deserts or seas, predict agricultural seasons, cast horoscopes, and solve complex mathematical problems. This integration reflected the Islamic Golden Age's worldview that saw no contradiction between scientific inquiry and religious faith, between artistic beauty and practical utility. The astrolabe stood as a physical manifestation of this integrated understanding, a brass embodiment of the idea that through careful observation, precise measurement, and thoughtful design, humans could comprehend the patterns of the cosmos and align their lives with its rhythms. Meanwhile, high on a mesa in what is now New Mexico, the ancestral Pueblo peoples were achieving celestial precision through an entirely different medium, the dramatic interplay of sunlight and shadow on stone. The Sun Dagger site at Choco Canyon represents one of the most elegantly simple yet profoundly sophisticated astronomical devices ever created. Imagine a spiral petroglyph carved into a vertical rock face, seemingly just one of many such rock art panels throughout the Southwest. But this particular spiral possesses a secret that lay hidden for centuries. It functions as an incredibly precise celestial calendar, marking the solstices, equinoxes, and even the complex 18.6-year lunar cycle through carefully engineered light patterns that would put many modern instruments to shame. The genius of this device lies in its elegant simplicity and breathtaking precision. 3 large stone slabs were carefully positioned on the overhanging cliff above the spiral, their placement so exact that they create specific light patterns during key astronomical events. During the summer solstice, as the sun reaches its highest point in the sky, a single dagger of sunlight pierces directly through the center of the spiral, bisecting it with such perfect alignment that it seems almost supernatural. 6 months later, during the winter solstice, 2 distinct daggers of sunlight appear, perfectly framing the spiral on either side as if highlighting its significance. The equinoxes produce their own unique signature, a shadow bar that cleanly divides the spiral into equal halves, marking the moment when day and night stand in perfect balance. These aren't rough approximations but precise alignments achieved through what must have been generations of careful observation and meticulous engineering. What makes the Sun Dagger truly extraordinary is its ability to track the moon's complex cycle, something that requires sophisticated understanding of celestial mechanics. The moon doesn't simply follow the sun's path. It has its own 18.6-year cycle of rising and setting positions, with major and minor standstills marking the extreme points of this pattern. The ancestral Pueblo astronomers designed their stone calendar to track this lunar cycle as well. During a major lunar standstill, a distinctive pattern of light and shadow interacts with the spiral in a unique way that occurs only once every 18.6 years. The fact that they not only recognized this long-term cycle, but engineered a permanent structure to mark it demonstrates astronomical knowledge that rivals many modern observatories in its conceptual sophistication. The construction of this celestial calendar required more than just casual observation. It represents a sustained scientific project spanning generations. The ancestral Puebloans would have needed to track celestial movements for decades to recognize the patterns they were encoding in stone. The placement of the rock slabs wasn't accidental. Each one was carefully positioned to create the specific light effects at precisely the right moments. This required advanced understanding of geometry, solar angles, and the changing positions of celestial bodies throughout the year. The engineers would have had to calculate the exact positions where sunlight would fall at specific times, and then position the stones to create the desired patterns, a task that would challenge modern engineers even with computer modeling. The cultural significance of this device extends far beyond simple timekeeping. For the ancestral Pueblo peoples, these celestial events weren't just markers of seasonal change. They were sacred moments that connected their community to the cosmic order. The appearance of the sun dagger through the spiral likely signaled the timing of important ceremonies, agricultural activities, and social gatherings. The precision of the alignments would have reinforced the authority of calendar priests who could predict these events with accuracy, while also creating powerful communal experiences as people gathered to witness these celestial dramas unfold on the rock face. The device served as both a practical calendar and a profound spiritual tool that connected daily life to the rhythms of the cosmos. The discovery of the sun dagger's true function came surprisingly recently, in the 1970s, when researchers who had been studying the site for years finally witnessed the solstice phenomenon. This relatively recent recognition highlights how easily such sophisticated knowledge can be lost and then rediscovered. The site had been known to archaeologists for decades, but its function as a precise astronomical instrument wasn't understood until someone happened to be present at exactly the right moment on the summer solstice. This reminds us that many ancient technologies may still be hiding in plain sight, their functions misunderstood or overlooked because we haven't witnessed them operating under the specific conditions for which they were designed. The preservation of this knowledge across generations without written records speaks to the sophistication of oral traditions and observational practices among the ancestral Pueblo peoples. The precise astronomical information encoded in the sun dagger would have been maintained and passed down through careful observation and oral teaching, creating a living tradition of celestial knowledge that sustained their culture for centuries. This challenges the notion that advanced astronomical understanding requires written records or complex mathematics. The Pueblo astronomers achieved remarkable precision through careful observation, pattern recognition, and ingenious engineering using the materials available to them. What's particularly inspiring about the sun dagger is its continued operation centuries after its creators departed the region. The device still marks the solstices and equinoxes with undiminished accuracy, a testament to the durability of its design and the permanence of the celestial cycles it tracks. Unlike mechanical devices that wear out or require maintenance, this stone calendar continues to function exactly as intended, connecting modern observers to the ancient astronomers who designed it. This endurance represents a different approach to technology, one that works with natural cycles rather than against them, that uses permanent materials rather than replaceable parts, and that creates instruments that grow more accurate with time rather than deteriorating. The sun dagger stands as powerful evidence that advanced astronomical knowledge emerged independently across multiple cultures. each developing unique solutions to the universal human desire to understand and measure time. While the Greeks were building geared mechanisms and the Maya were constructing stone observatories, the ancestral Pueblo peoples were achieving similar precision through the clever manipulation of sunlight and shadow on carved stone. This diversity of approaches enriches our understanding of human ingenuity, showing that technological sophistication can take many forms, from the mechanical complexity of bronze gears to the elegant simplicity of aligned stone slabs, creating perfect patterns of light that mark our place in the cosmic dance. Meanwhile, as Islamic scholars perfected their astrolabes and ancestral Pueblo astronomers tracked celestial cycles in stone within the secluded walls of medieval European monasteries, a different kind of timekeeping revolution was quietly unfolding, one driven by the relentless rhythm of prayer rather than the movements of stars. The development of monastic water clocks represents a fascinating chapter in horological history where spiritual necessity became the mother of mechanical invention. These weren't simply timekeeping devices. They were complex mechanical orchestras that synchronized entire communities with divine schedules, transforming the abstract concept of time into a tangible, audible presence that governed every aspect of monastic life. The driving force behind these technological marvels was the canonical hours, 7 distinct prayer periods that divided both day and night into sacred intervals. This rigid schedule demanded precision that simple sundials or water clocks couldn't provide, especially during long winter nights or cloudy days when traditional timekeeping methods failed. Monastic communities responded by developing increasingly sophisticated water-powered mechanisms that could maintain accurate time measurement regardless of weather conditions or season. The most advanced versions featured constant flow systems using multiple chambers and overflow mechanisms that maintained steady water pressure, ensuring the timing remained consistent hour after hour, day after day. Some incorporated mercury instead of water in their regulators, the dense liquid being less affected by temperature changes that could alter water's viscosity and thus its flow rate, demonstrating an early understanding of fluid dynamics that would only be formally explained centuries later. What made these clocks truly extraordinary were their automated signaling systems. Elaborate gear trains translated the steady flow of water into precisely timed mechanical actions that would strike bells, move indicators, or even activate entire carillons that could be heard throughout the monastery and surrounding villages. The technology behind these striking mechanisms was remarkably sophisticated cam systems that could produce different strike patterns for different hours, release mechanisms that prevented false strikes, and reset systems that prepared the mechanism for the next cycle. This automation ensured that the entire community, from the abbot to the newest novice, would be summoned to prayer at exactly the right moments, maintaining the strict temporal discipline that defined monastic life. The sound of these bells became the heartbeat of medieval communities, regulating not just prayer but market hours, court sessions, and civic activities in the towns growing around monastic centers. The most ambitious monastic clocks evolved into complete astronomical theaters that blended timekeeping with cosmic representation. These magnificent devices often featured moving models of the sun, moon, and planets that traced their paths through the zodiac, displayed dials showing the phases of the moon and the positions of important stars, and calendars that tracked religious feasts and saints' days. Some included elaborate automata mechanical figures of saints, angels, or biblical characters that would perform at specific times, acting out religious scenes that both educated and inspired the observers. The clock at the Abbey of St. Albans in England, designed by the remarkable monk Richard of Wallingford in the 14th century, featured an enormous astronomical dial showing the movements of celestial bodies, a wheel of fortune that turned continuously, and even a mechanism that predicted eclipses with considerable accuracy. This integration of time measurement with cosmic modeling created a physical representation of the medieval world, where earthly time and celestial motion were intimately connected through divine order. The technological innovations emerging from these monastic workshops didn't just serve spiritual purposes, they represented crucial stepping stones in the development of mechanical timekeeping. The verge and foliate escapement, that fundamental component that regulates energy release in mechanical clocks, likely evolved from mechanisms first developed in these monastic water clocks. The intricate gear trains that translated the slow rotation of water wheels into the faster motions needed for striking mechanisms and astronomical displays pushed the boundaries of medieval metallurgy and precision craftsmanship. The need to maintain these complex devices led to improved tools and techniques for metalworking, gear cutting, and mechanical assembly. This monastic horological tradition essentially created the knowledge base and skilled craftsmen that would eventually give rise to the public clockmaking industry as European towns began installing their own tower clocks in the 14th and 15th centuries. The social impact of these timekeeping systems extended far beyond monastery walls. As towns grew around monastic centers, the regulated time of the monastery began to influence secular life as well. The bells calling monks to prayer also signaled the opening of markets, the changing of guards, and the hours for public business. This synchronization of communal activities created a more organized, predictable social rhythm that contrasted with the more fluid time consciousness of earlier medieval life. The monastic emphasis on punctuality and schedule gradually seeped into the broader culture, helping to create the time-disciplined society that would eventually characterize the modern world. The monasteries essentially functioned as medieval research and development centers where the technology of time measurement was refined and perfected before spreading to the wider society. What's particularly remarkable about these monastic achievements is that they occurred during what we often mistakenly call the Dark Ages, a period traditionally viewed as technologically stagnant. The reality revealed by these sophisticated water clocks shows continuous innovation and mechanical sophistication that would eventually flower into the mechanical clock tradition that transformed European society. The monks designing these devices were not merely copying classical knowledge but building upon it, solving practical problems with creativity and engineering skill that pushed the boundaries of what was possible with medieval technology. Their work preserved classical mechanical knowledge while adding new innovations that would eventually help launch Europe's technological ascendancy. The legacy of these monastic timekeepers endures in our modern relationship with time itself. The division of the day into equal hours, the concept of scheduling activities according to a mechanical timekeeper, even the idea of being on time, all have roots in the temporal discipline developed in medieval monasteries. These water-powered marvels represent a crucial transition between the celestial timekeeping of antiquity and the mechanical timekeeping of the modern world, a bridge between observing nature's rhythms and imposing human-made order on the flow of time. The quiet, constant dripping of water in monastery courtyards ultimately gave rise to the ticking of clocks that would eventually regulate the entire world, demonstrating how spiritual devotion could drive technological innovation that would transform human civilization. As the resonant bells of European monastic clocks echoed across medieval towns, in the heart of the expanding Ottoman Empire, a different kind of timekeeping precision was emerging from the minarets and courtyards of magnificent mosques. Here, time wasn't measured by mechanical gears or water flow alone, but by the precise movement of celestial bodies, governed by the sophisticated science of timekeeping experts known as muvakits. These scholars stood at the fascinating intersection of Islamic tradition and astronomical innovation, developing methods and instruments of such remarkable accuracy that they could determine prayer times to within minutes across the vast Ottoman territories from the Balkans to North Africa. The challenge facing these timekeepers was considerably more complex than simply dividing the day into equal hours. Islamic prayer times are determined by specific solar positions that change daily and vary by location. Fajr prayer begins at true dawn when light first appears on the horizon. Dhuhr occurs when the sun passes its zenith, Asr when shadows reach certain lengths, Maghrib immediately after sunset, and Isha when darkness is complete. These aren't fixed clock times but astronomical events that shift throughout the year and differ at every latitude. The muvakids responded to this challenge by creating specialized timekeeping facilities called muvakithanes, often located within mosque complexes, where they performed precise calculations using a remarkable array of instruments that blended ancient wisdom with emerging mechanical technology. At the heart of their toolkit were beautifully crafted astrolabes and quadrant instruments, but adapted for specifically Islamic timekeeping needs. They developed specialized versions with scales calibrated for prayer time calculations, including the Rub al-Muqantarat, a type of quadrant that could directly determine prayer times based on solar altitude. These brass instruments featured intricate engravings that incorporated both astronomical coordinates and religious information, with some advanced models capable of handling the complex calculations needed for the 5 daily prayers across different seasons. The muvakids also used precise sundials designed specifically for mosque courtyards, often monumental in scale and calibrated for their exact geographic location, with some featuring multiple gnomons or curved surfaces to account for the changing solar declination throughout the year. The mathematical sophistication behind these calculations was truly extraordinary. Muvakids had to account for atmospheric refraction, the bending of sunlight near the horizon that affects the apparent timing of sunrise and sunset. They developed correction tables based on careful observation that could adjust for this phenomenon, ensuring that prayer times were determined based on the sun's actual position rather than its apparent one. They also created complex algorithms for calculating the true noon, which varies throughout the year due to the equation of time, the discrepancy between solar time and clock time caused by the Earth's elliptical orbit and axial tilt. These calculations required advanced understanding of spherical trigonometry and celestial mechanics that rivaled contemporary European astronomy. Some major Ottoman mosques featured elaborate mechanical clocks that automated the timekeeping process while maintaining astronomical accuracy. The most sophisticated of these were weight-driven mechanisms that incorporated equation of time corrections and could display both equal hours and seasonal hours simultaneously. The famous clock in the courtyard of the Yeni Mosque in Istanbul, for instance, featured multiple dials showing prayer times, ordinary clock time, and astronomical information, all driven by a sophisticated movement that required adjustment only once every few days. These mechanical marvels often included automatic signaling systems that would raise flags, sound gongs, or even trigger light displays to announce prayer times to the surrounding community. The social role of the muvakid extended far beyond technical timekeeping. These scholars were respected members of their communities, often serving as teachers, astronomers, and religious advisors. Their muvakithanes functioned as centers of learning where students could study mathematics, astronomy, and the scientific traditions of Islam. The precise timekeeping they provided helped synchronize daily life across Ottoman cities, with merchants scheduling markets around prayer times, courts holding sessions according to established timetables, and the entire community participating in the rhythmic pattern of daily worship that structured Ottoman society. What's particularly impressive about this tradition is how it maintained its accuracy across the diverse geography of the Ottoman Empire. Muvakits developed methods for determining local prayer times that accounted for differences in longitude and latitude, creating standardized calculation procedures that could be taught to timekeepers in distant provinces. They produced extensive Zij or astronomical handbooks that contained tables for calculating prayer times, calendar information, and stellar positions for various cities throughout the empire. This systematic approach to timekeeping created a network of synchronized religious observance across thousands of miles, all based on precise astronomical observation and calculation. The legacy of Ottoman timekeeping represents a remarkable fusion of scientific precision and religious practice that challenges simplistic narratives about the relationship between science and religion. The Muvakits saw their astronomical work as a form of religious devotion, an effort to understand Allah's creation more perfectly and to worship according to precisely determined times. Their instruments, with their beautiful craftsmanship and intricate engravings often featuring religious inscriptions, embodied this fusion of scientific and spiritual values. This tradition demonstrates how religious requirements can drive scientific innovation rather than hinder it, creating a sophisticated timekeeping culture that maintained its accuracy and relevance for centuries while contributing significantly to the development of astronomy and horology in the Islamic world. As Europe emerged from the Middle Ages, a new horological revolution began to chime from the towers of its greatest cities, transforming public squares into theaters of cosmic wonder. Renaissance astronomical clocks represented far more than timekeeping devices. They were mechanical embodiments of the entire known universe, crafted in brass and iron to make the mysteries of the cosmos visible to all. These monumental creations emerged during a period of unprecedented intellectual ferment, when the rediscovery of classical knowledge collided with new scientific inquiry, and clockmakers became the era's rock stars, artisans whose mechanical genius could literally bring the heavens down to earth for public admiration. The Prague astronomical clock, installed in 1410 on the Old Town Hall, stands as perhaps the most magnificent example of this horological artistry. To stand before it is to witness an entire medieval world view in motion, a breathtaking symphony of gears and escapements that tracks not just hours, but the very dance of the cosmos itself. The clock's main dial is a masterpiece of information density, showing 24-hour time, the position of the sun and moon in the zodiac, and the date simultaneously. Above this, two smaller dials display Old Czech time and Babylonian time, the latter representing unequal hours that varied in length with the seasons. The astronomical dial alone contains concentric rings showing sidereal time, the sun's position on the ecliptic, and the phases of the moon, which rotates to show its current appearance in the night sky. This complexity wasn't merely decorative. It provided a complete astronomical reference for a city that valued both scientific knowledge and practical timekeeping. What truly captivates visitors even today is the clock's theatrical performance on the hour, when a mesmerizing procession of automated figures springs to life. The 12 apostles parade past windows while skeletal death tolls his bell. A Turk shakes his head in defiance, and vanity admires himself in a mirror, each figure representing medieval concerns about mortality and morality. This blend of mechanical precision and allegorical theater perfectly captures the Renaissance spirit, where scientific advancement coexisted with religious symbolism, and public timekeeping served both practical and pedagogical purposes. The clock didn't just tell time, it told a story about humanity's place in the cosmic order, reminding viewers of both the marvels of creation and the transience of earthly existence. The mechanical sophistication behind these astronomical marvels represented quantum leaps in precision engineering. clockmakers developed new types of gear trains that could accurately model the irregular motions of celestial bodies, including the moon's varying speed and the retrograde motion of planets. The prog clock's mechanism for showing the moon's phases is particularly ingenious, using a complex arrangement of gears that slowly rotates a black and gold sphere to accurately display the lunar cycle. These mechanisms had to account for the eccentricities of the Ptolemaic system, the prevailing cosmological model that placed Earth at the center of the universe with planets moving in complex epicycles. Creating mechanical equivalents of these mathematical concepts required both theoretical understanding and practical ingenuity of the highest order. Across Europe, other cities commissioned their own astronomical masterpieces, each with unique features reflecting local priorities and technological capabilities. The clock in the Cathedral of Strasbourg, completed in 1574, featured an automated calendar that could accurately calculate the date of Easter, a complex computation that depends on both solar and lunar cycles. The Wells Cathedral clock in England, built around the same period, included mechanisms that showed the motion of the sun and moon against the stars and featured jousting knights that charged each other every hour. These public clocks became sources of civic pride and technological showcase, demonstrating a city's wealth, learning, and engineering prowess to visitors and residents alike. The creation of these monumental timepieces required collaboration among diverse experts: master clockmakers who designed the mechanisms, blacksmiths who forged the iron frames, brass workers who crafted the delicate gears, astronomers who provided the mathematical calculations, and artists who created the painted dials and sculpted figures. The astronomical dials themselves served as educational tools, making complex celestial concepts visible and understandable to people who might never study astronomy formally. By watching the slow movement of the sun through the zodiac or the changing phases of the moon, ordinary citizens could develop a more sophisticated understanding of cosmic cycles and their relationship to daily life. These clocks also played a crucial role in the standardization of time within growing urban centers. As cities expanded and commercial activities became more complex, the need for synchronized timekeeping became increasingly important. The astronomical clock provided a reliable reference that could regulate market hours, court sessions, and public events, creating a shared temporal framework that helped coordinate urban life. The public nature of these timepieces, positioned high on town halls and cathedrals where everyone could see them, democratized access to precise time, which had previously been available only to the wealthy or educated who could afford personal sundials or water clocks. The legacy of these Renaissance marvels extends far beyond their historical period. The technological innovations developed for astronomical clocks, particularly the precision gear cutting and escapement mechanisms, directly contributed to the development of more accurate domestic timepieces and navigational instruments. The conceptual breakthrough of creating mechanical models of natural phenomena paved the way for later scientific instruments and even early computing devices. Perhaps most importantly, these clocks helped foster a new way of thinking about the universe as operating according to regular, measurable principles that could be understood through observation and represented through mechanical analogy, a worldview that would eventually lead to the scientific revolution. While European clockmakers were assembling their intricate brass mechanisms and Ottoman timekeepers were calculating prayer times with precision instruments, across the vast expanse of the Pacific Ocean, an entirely different approach to time and navigation was evolving, one that required no metal, no gears, and no written records, yet achieved accuracy that would astonish modern navigators. Polynesian voyagers developed what might be considered the most sophisticated mental timekeeping and navigation system ever created, transforming the entire Pacific into a precisely mapped seascape using nothing but memory, observation, and generations of accumulated knowledge. Their achievement represents perhaps the ultimate fusion of time and space measurement, where understanding when was inseparable from knowing where, all encoded in oral traditions and memory devices of remarkable complexity. The foundation of this system was the star compass, a mental construct that divided the horizon into 32 directional points, each marked by specific stars that rose and set at those precise locations. But this was no simple directional tool. It was a dynamic, four-dimensional map that accounted for both position and time. Navigators knew exactly which stars would appear at which points on the horizon at different times of night and different seasons of the year. They understood that as night progressed, the star paths would rotate around the celestial pole, creating moving reference points that could be used to maintain course through the darkness. This mental star map was so precise that experienced navigators could maintain their heading even during overcast nights by sensing the swell patterns that continued to reflect the prevailing wind directions aligned with star paths. What made this system truly extraordinary was its integration of multiple timekeeping methods that operated simultaneously. Navigators tracked the passage of night since departure, the phases of the moon, and the changing positions of stars throughout the year, all without written calendars or mechanical devices. They used the rising and setting of specific stars as seasonal markers that indicated when certain voyages should be undertaken, when winds would shift, and when target islands would be most accessible. The star known as Pleiades, for example, signaled the beginning of the traditional voyaging season when weather patterns were most favorable for long-distance travel. This celestial calendar was memorized so thoroughly that navigators could determine their approximate longitude based on how much the star configurations had changed since departure. The physical manifestation of this knowledge appeared in the form of navigation sticks, carefully carved wooden implements that served as memory aids rather than direct measuring instruments. These sticks didn't contain written information but featured notches, bends, and attachments that helped navigators recall complex sequences of star paths, swell patterns, and island references. Each bend might represent a particular star course to be followed for a certain number of nights, while shells attached with cord might indicate specific islands or sea marks along the route. These devices were highly personal, with each navigator creating his own memory aids based on years of training and experience, yet all working within the same shared framework of navigational knowledge that had been refined over centuries. The timekeeping precision required for successful voyaging was nothing short of astonishing. Navigators needed to maintain a mental dead reckoning of their position that incorporated speed, direction, and time elapsed, all without instruments. They estimated speed by observing the patterns of bubbles and debris passing the canoe, the feel of the waves against the hull, and the sound of water moving along the sides. They kept track of time through the number of star cycles observed, the changing position of specific stars relative to the horizon, and even the biological rhythms of their own bodies conditioned by years of training. This mental calculation of position over time allowed them to navigate to tiny islands thousands of miles apart with reliability that modern sailors using charts and GPS still find difficult to comprehend. The settlement pattern of the Pacific stands as ultimate proof of this system's effectiveness. The Polynesian Triangle stretches from Hawaii in the north to New Zealand in the southwest to Easter Island in the southeast, an area larger than all the continents combined. Within this vast expanse, navigators found and settled hundreds of islands, some no larger than a few square miles, separated by open ocean distances of thousands of miles. The timing of these voyages was critical. They had to arrive during seasons when winds and currents were favorable for both travel and initial settlement activities. The fact that they could consistently make these journeys, often against prevailing winds using sophisticated tacking techniques, demonstrates a level of navigational and temporal precision that rivaled anything being done in other parts of the world at the time. This knowledge system was preserved and transmitted through elaborate oral traditions that functioned as living libraries of navigational information. Chants and stories encoded star paths, sailing directions, island characteristics, and seasonal information in poetic form that could be memorized and passed down through generations. Young navigators would spend years learning these chants and their meanings, then decades gaining practical experience before being entrusted with leading voyages. The training was so thorough that when traditional Polynesian navigation was revived in the 1970s, navigators who had learned from the last remaining traditional experts were able to make successful long-distance voyages using only these ancient methods, proving that the knowledge, when properly preserved, remained viable centuries after its original development. The comparison with contemporary European navigation methods reveals fascinating differences in approach. While European sailors were developing increasingly complex instruments, astrolabes, cross-staffs, and eventually marine chronometers, Polynesian navigators were perfecting their mental models and sensory awareness. European navigation tended to separate time measurement from position finding, eventually requiring the development of the marine chronometer to solve the longitude problem. Polynesian navigation integrated time and space into a unified mental model where knowing when certain stars would appear was inseparable from knowing where you were relative to your destination. Both systems achieved remarkable accuracy, but through completely different technological paths, one external and mechanical, the other internal and cognitive. The enduring legacy of this wayfinding tradition challenges our modern assumptions about what constitutes technology and measurement. In a world increasingly dependent on digital devices and satellite signals, the Polynesian achievement reminds us that the human mind, properly trained and equipped with deep knowledge, can accomplish feats of precision that rival the most sophisticated instruments. Their navigation system represents a different kind of technological sophistication, one based on intimate knowledge of natural patterns, refined observation skills, and mental models of breathtaking complexity. This approach allowed them to settle the last major region of our planet without written records, metal tools, or mechanical devices, using instead the greatest computer ever created, the human mind, trained through generations of accumulated wisdom and practical experience. While the Polynesians were mastering mental navigation across vast ocean distances, back in the heart of the Roman Empire, timekeeping took on a distinctly public and practical character that reflected Rome's obsession with order, administration, and military precision. The Romans didn't just observe time, they organized it, regimented it, and built it into the very infrastructure of their cities and the operations of their legions. Their approach to horology was characteristically pragmatic. They adopted Greek astronomical knowledge and engineering principles, then scaled them up for public utility and imperial administration in ways the Greeks had never imagined. The result was a comprehensive timekeeping system that helped synchronize the daily life of millions across the vast expanse of the empire, from the misty frontiers of Britain to the sun-baked cities of North Africa. The most spectacular manifestation of Roman timekeeping ambition was undoubtedly the Solarium Augusti, a monumental sundial complex in the Campus Martius that dwarfed any previous timekeeping installation. At its heart stood a red granite obelisk imported from Egypt, soaring 100 feet into the Roman sky. This massive needle functioned as the gnomon, casting a shadow that swept across an enormous paved area, marked with a bronze meridian line and elaborate marble panels indicating hours, seasons, and zodiac signs. The scale was deliberately imperial. This wasn't just a timekeeping device, but a powerful symbol of Augustus's ability to bring order to both time and territory. The obelisk's shadow didn't merely indicate the hour. It marked the sun's progress through the year, with the length of the shadow showing the season and its position indicating the date with precision that guided both agricultural planning and religious ceremonies. The entire installation functioned as a civic calendar and clock combined, making celestial time visible to all citizens in the heart of their capital. For nighttime and cloudy weather, the Romans developed water clocks of remarkable sophistication that built upon Greek designs but added characteristically Roman improvements in scale and practicality. The public clepsydras found in forums and bath complexes featured multiple tanks and overflow systems that maintained constant water pressure, ensuring consistent time measurement regardless of how much water remained in the reservoir. Some incorporated elaborate float mechanisms connected to indicator hands that moved across dials, while others used the rising water level itself to trigger bells or other audible signals at specific intervals. The most advanced versions included gear systems that could adjust for the changing length of daylight hours throughout the year, a crucial feature in a society that divided both day and night into 12 equal hours regardless of season, making winter hours shorter than summer ones. This mechanical compensation demonstrated a sophisticated understanding of both astronomy and practical engineering that allowed these clocks to maintain accuracy year-round. The Roman military took timekeeping to another level of precision, understanding that coordinated operations across vast distances required reliable temporal coordination. Legionary fortresses throughout the empire featured standardized sundials positioned in central courtyards, allowing soldiers to synchronize watch changes, drills, and patrol schedules. Water clocks were used during nighttime guard duties, with specially trained soldiers responsible for maintaining and monitoring these devices to ensure sentries changed at precisely the right moments. The army even developed portable timekeeping devices for campaigns, compact sundials with adjustable gnomons that could be set for different latitudes, and small water clocks that could operate during marches. This temporal discipline gave Roman forces a significant advantage over opponents who operated with less precise scheduling, allowing complex multi-unit maneuvers and coordinated attacks that often decided battles. Roman timekeeping technology also reflected their talent for standardization and mass production, the same skills that allowed them to produce identical pottery, bricks, and weapons across their empire. Portable sundials became surprisingly common among the wealthy and official classes, with archaeological examples found from Britain to Jordan showing remarkably consistent designs. These personal timepieces often featured multiple dials showing both equal and seasonal hours, with some incorporating miniature compasses to ensure proper orientation. The most sophisticated portable models were adjustable for different latitudes, allowing officials traveling across the empire to maintain accurate timekeeping regardless of their location. This democratization of time measurement among the administrative class helped synchronize government operations and commercial activities across vast distances. The social impact of this public timekeeping infrastructure transformed daily life in Roman cities. The division of daylight into 12 hours created a standardized framework for business hours, court sessions, and public activities. The famous phrase, "at the first hour" or "at the third hour," appears constantly in Roman literature and legal texts, indicating how thoroughly this temporal organization had penetrated society. The sounding of bells or horns at specific hours regulated market activities, school sessions, and even the opening of public baths. This created a more regimented, synchronized urban existence that contrasted with the more fluid time consciousness of rural areas. a distinction that would persist for centuries and eventually evolve into the modern conception of standardized time. What's particularly fascinating about Roman horology is how it represents both technological adoption and innovation. The Romans freely acknowledged their debt to Greek astronomy and engineering. Many of their best clockmakers were Greek slaves or freedmen, but they applied this knowledge with characteristically Roman practicality and scale. While Greek water clocks were often elegant scientific instruments found in philosophical schools, Roman versions were robust public utilities designed for durability and daily use. While Greek sundials were frequently small and portable, the Romans built them into the very architecture of their cities on a monumental scale. This transformation of timekeeping from philosophical pursuit to practical infrastructure represents one of Rome's most enduring contributions to Western civilization, the idea that precise time measurement should be publicly available, systematically organized, and integrated into the daily functioning of society. This conceptual framework would eventually shape the development of public clock towers in medieval Europe and ultimately lead to the global time standardization we take for granted today. While Roman timekeeping was monumental and public, designed to organize entire cities and armies, the Byzantine Empire that followed refined time measurement into something both personal and precise, creating instruments of such sophistication that they could accompany an individual anywhere across their vast territories. Byzantine portable sundials represent a fascinating evolution in horology, the transformation of timekeeping from fixed public infrastructure to personal precision instrument. These weren't simple shadow catchers but compact marvels of engineering that incorporated multiple innovations to maintain accuracy regardless of location or season, effectively putting the equivalent of an astronomical observatory in the palm of one's hand. The true genius of these devices lay in their adaptability to different latitudes, a crucial feature for an empire that stretched from southern Italy to the Black Sea and from North Africa to the Middle East. Unlike fixed sundials calibrated for a specific location, these portable versions featured adjustable gnomons, the shadow-casting elements that could be set to the correct angle for whatever latitude the user found themselves in. Some models included intricate gear mechanisms that allowed the user to dial in their precise location using scales engraved around the device's circumference. This meant a merchant traveling from Constantinople to Alexandria could recalibrate his sundial upon arrival and continue to tell time with undiminished accuracy, a capability that would remain unmatched until the development of marine chronometers centuries later. Perhaps even more impressively, some advanced Byzantine sundials incorporated mechanisms to account for the equation of time, the discrepancy between apparent solar time shown by sundials and mean solar time used in mechanical clocks. This variation, caused by the Earth's elliptical orbit and axial tilt, means that sundials can be up to 16 minutes fast or slow compared to clock time at different times of the year. The fact that Byzantine engineers understood this phenomenon and developed mechanical compensations for it demonstrates astronomical knowledge and mathematical sophistication that we typically associate with much later periods. These equation of time mechanisms often took the form of specially shaped cam-like gears that would subtly adjust the sundial's reading throughout the year, effectively building celestial mechanics into portable timekeeping. The craftsmanship of these devices was extraordinary, blending scientific precision with artistic beauty. Artisans worked with materials like ivory, brass, and silver, creating instruments that were both functional tools and status symbols. The engraved scales on the best examples show markings accurate to within fractions of a degree, achieved through painstaking handwork without magnification. Some featured multiple concentric dials showing different time systems' seasonal hours that varied in length throughout the year, equal hours like we use today, and even liturgical hours important for religious observance. The precision of these engravings allowed users to determine time to within minutes when the devices were properly oriented and calibrated, a level of accuracy that would satisfy most modern timekeeping needs. The portability of these sundials made them invaluable across Byzantine society. Military commanders used them to coordinate troop movements and watch schedules during campaigns, ensuring synchronization across dispersed units. Merchants relied on them to time market activities and business meetings in different cities, their portable nature allowing them to maintain consistent scheduling throughout their travels. Government officials carried them on diplomatic missions, using the devices not just for timekeeping but as demonstrations of Byzantine technological sophistication. Even religious pilgrims found them essential for maintaining prayer schedules during long journeys. This widespread adoption shows how thoroughly precise time measurement had penetrated Byzantine culture, becoming a tool for practical daily use rather than just scientific or religious application. The design of these portable sundials reveals much about Byzantine technological priorities and capabilities. Many incorporated magnetic compasses centuries before they became common in Western Europe to ensure proper orientation toward true north. Some featured built-in plumb bobs or bubble levels to guarantee they were positioned correctly. The most sophisticated models included instruction manuals engraved directly on their surfaces, with detailed explanations of how to set them for different latitudes and seasons. This attention to user-friendliness suggests these weren't just specialist instruments for astronomers but practical tools designed for educated laypeople who needed reliable timekeeping in their professional activities. What's particularly remarkable about these devices is how they represent a different technological trajectory from the water clocks and geared mechanisms developing elsewhere. While others were pursuing complex mechanical solutions to timekeeping, Byzantine engineers achieved similar precision through refined geometry and precision craftsmanship applied to the ancient principle of the sundial. This approach created instruments that required no power source, never needed winding, and maintained their accuracy indefinitely, advantages that mechanical clocks wouldn't match for centuries. The survival of many examples in archaeological context shows they were built to last, with materials and construction techniques that have preserved their functionality across a millennium. The legacy of these portable marvels extends beyond their immediate timekeeping function. They represent the democratization of precise time measurement, putting capabilities that had previously required fixed installations and specialist knowledge into the hands of mobile individuals. This portability reflected the increasingly mobile nature of Byzantine society, with its extensive trade networks, diplomatic corps, and military deployments across vast distances. The devices also served as vehicles for transmitting astronomical and geographical knowledge throughout the educated classes, their engraved scales teaching users about latitude, solar motion, and time measurement principles even as they served practical purposes. In many ways, these sophisticated sundials were the smartphones of their day, compact, personal devices that integrated multiple functions and kept their users connected to standardized time regardless of where they traveled throughout the empire. While European monks were perfecting their water-powered horological wonders and Byzantine travelers consulted their portable sundials in medieval China, timekeeping took an entirely different sensory direction, one that measured hours not through the flow of water or the movement of shadows, but through the steady, fragrant burn of specially formulated incense. These ingenious devices transformed time measurement into an aromatic experience, where the passage of hours was marked by shifting scents and the gradual consumption of precisely engineered combustible materials. The Chinese incense clock represents a fascinating alternative approach to horology that achieved remarkable precision through chemical knowledge and material science rather than mechanical complexity. The foundation of these timekeepers lay in the extraordinary consistency of their burning rates, achieved through centuries of experimentation with different ingredients and formulations. Artisans developed complex recipes that blended aromatic woods like sandalwood and agar wood with binding agents such as honey or fruit extracts, and sometimes even added mineral powders to regulate combustion speed. The most precise incense sticks could burn at consistent rates accurate to within minutes over several hours, an achievement that required deep understanding of how different materials affected combustion properties. This chemical engineering was so refined that craftsmen could produce incense that burned at precisely predetermined rates, whether 1 inch per hour for shorter time periods or much slower for extended duration timekeeping. The reliability of these formulations meant that an incense clock could maintain its accuracy day after day, requiring only that someone light the next stick at the appropriate moment. Some of the most elaborate incarnations of this technology took the form of intricate incense seals, flat trays or plates with grooves cut into them in complex patterns that often resembled Chinese characters or symbolic designs. The craftsman would carefully fill these grooves with powdered incense of a precisely calibrated composition, then light it at the starting point. As the incense smoldered along the predetermined path, it would trace a glowing line through the pattern, with different sections representing different time intervals. The complexity of these designs allowed for remarkable sophistication. A single seal might incorporate multiple time scales, with inner rings marking quarter hours, middle rings tracking hours, and outer circles indicating longer periods. The most ambitious examples featured designs that could burn for 12 hours or more, providing continuous time measurement through the full day-night cycle. The sensory dimension of these timekeepers added a unique layer to their functionality. Sophisticated versions used different incense formulations along the burning path that released distinct aromas at specific times, creating a scented calendar that could signal different activities throughout the day. A government official might recognize the shift from sandalwood to lotus scent as indicating the mid-morning break, while the appearance of chrysanthemum fragrance might mark the appropriate time for afternoon meditation. This multisensory approach made these clocks particularly valuable in religious contexts where specific scents were associated with different rituals or prayer times, and in imperial courts where the appearance of certain aromas signaled the progression of ceremonial activities. The mechanical sophistication of some incense clocks rivaled their European water-powered counterparts in ingenuity, if not in mechanical complexity. Elaborate models incorporated weights, strings, and metal balls that would be released as the incense burned down. A common design featured a lightweight metal ball suspended over the incense stick by a thread that would eventually be burned through, causing the ball to drop into a metal bowl with a distinctive chime. More complex arrangements might have multiple strings with weights positioned at different points, creating a sequence of auditory signals at predetermined intervals. Some surviving examples from the Song dynasty even feature geared mechanisms that were triggered by the progressive burning, showing how incense timekeeping eventually merged with mechanical innovation to create hybrid devices of remarkable sophistication. The practical applications of these aromatic timepieces extended throughout Chinese society, each adapted to specific needs and contexts. In Buddhist monasteries, large incense clocks helped regulate the daily schedule of prayers and meditation sessions, their gentle fragrance creating an atmosphere conducive to spiritual practice. Physicians used smaller, more precise versions to time medical procedures and monitor the boiling of herbal preparations where exact timing was crucial for efficacy. Scholars employed desktop models to manage their study sessions, while the imperial court maintained magnificent examples that coordinated the complex schedule of ceremonies, audiences, and administrative activities. The portability and reliability of incense clocks made them particularly valuable for travel, as they required no water source, maintained accuracy regardless of motion, and could operate in any weather conditions. What makes these devices particularly impressive from a modern perspective is the scientific understanding they represent. The consistent burning rates required precise control over multiple variables: the composition and particle size of the incense materials, the density of compression, the cross-sectional area of the incense stick or powder trail, and even environmental factors like humidity that might affect combustion. Chinese incense makers developed standardized production methods that ensured consistency across different batches, and they understood how to compensate for atmospheric conditions that might affect burning speed. This knowledge represented a sophisticated practical understanding of combustion chemistry and material science that wouldn't be formally developed in the West for centuries. The cultural significance of incense clocks extended beyond their practical timekeeping function. They represented the integration of time measurement with aesthetic appreciation and spiritual practice, reflecting the Chinese philosophical concept of time as a continuous, flowing phenomenon rather than a series of discrete moments. The gradual, visible consumption of the incense provided a meditation on the passage of time itself, making these devices both practical tools and philosophical objects. The careful selection of fragrances connected timekeeping to seasonal awareness and natural cycles, with different scents being associated with different times of day, seasons of the year, or ceremonial purposes. The endurance of incense timekeeping tradition in China speaks to its effectiveness and cultural resonance. While mechanical clocks became increasingly available from the Ming Dynasty onward, incense clocks continued to be used in religious contexts, medical practice, and domestic settings where their quiet, aromatic operation was preferred over the audible ticking of mechanical devices. Even today, some traditional Chinese temples maintain the use of incense timekeeping for certain ceremonies, preserving a technological tradition that has continued for over a millennium. This longevity testifies to the sophistication of the original concept and the deep cultural appreciation for an approach to time measurement that engages multiple senses while maintaining remarkable precision through chemical rather than mechanical means. Meanwhile, in the lush river valleys and vibrant temple complexes of ancient India, timekeeping took on a profoundly spiritual dimension through the ingenious Ghatika Yantra water clocks that transformed the simple dripping of water into a sacred measure of existence itself. These weren't merely functional devices but instruments that embodied the Hindu philosophical concept of cyclical time, where the universe itself was believed to undergo creation, preservation, and dissolution in endless cycles. The Ghatika Yantra measured time in units called Ghatikas, each equivalent to 24 minutes, dividing the day and night into 60 equal segments that aligned with both astronomical observations and religious practices. This system reflected the sophisticated mathematical understanding of ancient Indian astronomers, who had calculated the length of the solar year with remarkable accuracy and developed complex calendrical systems that integrated lunar and solar cycles. The fundamental design of these water clocks displayed both simplicity and profound engineering insight. A typical Ghatika yantra consisted of a copper or ceramic pot with a precisely drilled hole at its base, placed carefully in a larger container of water. As water slowly seeped into the pot, it would eventually sink after exactly 1 Ghatika, at which point an attendant would empty it and begin the process again. The consistency of this measurement depended on numerous factors that ancient Indian engineers had mastered through careful experimentation. The size of the outflow hole had to be calibrated with extraordinary precision. Too large and the pot would fill too quickly, too small, and the measurement would extend beyond the required interval. Craftsmen developed standardized drilling techniques using copper wires and abrasive powders to create holes of consistent diameter, and some temple versions even featured replaceable orifice plates made of precious metals that resisted corrosion and maintained their calibration for decades. What truly set the most advanced Ghatika yantras apart was their incorporation of sophisticated float mechanisms and indicator systems that automated the timekeeping process. In these elaborate designs, the sinking pot would trigger a float mechanism that moved an indicator along a calibrated scale, showing the passage of time without requiring constant attention. Some versions used a series of pots arranged in sequence, where the filling of one pot would trigger the start of the next, creating a continuous time measurement system that could operate throughout the day and night. The most magnificent temple clocks featured musical elements, small hammers that would strike bronze bells or blow conch shells at the completion of each Ghatika, their sounds echoing through temple courtyards to mark the passage of time for both priests and the surrounding community. These auditory signals created a rhythmic soundscape that organized daily life around the temple's schedule of rituals and prayers. The accuracy of these devices depended on maintaining constant conditions that ancient timekeepers managed with remarkable sophistication. They understood that water temperature affected its viscosity and therefore its flow rate through the calibrated hole. To minimize this variation, temples often located their Ghatika yantras in underground chambers where temperatures remained stable throughout the year. Some versions used mercury instead of water in their measuring vessels, the dense liquid being less affected by temperature changes and providing more consistent flow rates. The quality of the water itself was carefully controlled, with attendants using filtered rainwater or water that had been allowed to settle to remove impurities that might clog the precise orifice. This attention to environmental factors demonstrates a practical understanding of fluid dynamics that wouldn't be formally described in scientific terms for centuries. In temple settings, these timekeeping instruments evolved into magnificent works of art that blended technological sophistication with spiritual symbolism. Elaborate Ghatika yantras featured sculpted figures of deities associated with time, such as Kala, the god of time, or the Navagraha representing the 9 planetary influences. Some included automated scenes from Hindu mythology that would activate at specific times, dancing figures, rotating models of the cosmos, or representations of the sun's chariot moving across the heavens. These artistic elements transformed the measurement of time from a mere practical necessity into a form of worship and meditation on the nature of time itself. The continuous, inexorable flow of water mirrored the concept of cyclical time in Hindu philosophy, where the universe undergoes endless cycles of creation and dissolution, each lasting billions of years. The practical applications of these timekeeping systems extended throughout ancient Indian society, each adapted to specific needs and contexts. In astronomical observatories, Ghatika yantras of exceptional precision helped astronomers time their observations of stellar transits and planetary movements, contributing to the development of sophisticated mathematical models of the cosmos. The famous astronomical school at Kerala used water clocks alongside elaborate stone instruments to make observations that would later influence both Islamic and European astronomy. In royal courts, these devices regulated the schedule of audiences, administrative functions, and ceremonial events, ensuring the smooth operation of government according to established timetables. Even in domestic settings, smaller versions helped households maintain their daily routines and prayer schedules, though these were naturally simpler than the magnificent temple installations. The mathematical principles underlying these water clocks reflected the advanced state of Indian science and mathematics during this period. Indian mathematicians had developed sophisticated understanding of geometry and calculus-like concepts that allowed them to calculate the flow rates through orifices of different sizes and shapes. They created detailed tables that specified the appropriate hole diameters for different types of pots and different liquids, accounting for factors like viscosity and temperature. The division of time into Ghatikas itself was mathematically elegant, fitting neatly into both the daily cycle and the larger astronomical cycles that Indian astronomers tracked with remarkable precision. This integration of mathematical theory with practical engineering created timekeeping devices that were both scientifically sophisticated and culturally meaningful. The enduring legacy of the Ghatika Yantra tradition can be seen in its influence on later timekeeping developments both within India and beyond. The concept of measuring time through the regulated flow of a substance would eventually evolve into the elaborate water clocks of the Islamic world and medieval Europe, though often without the philosophical depth that characterized the Indian approach. Within India itself, the tradition continued for centuries, with magnificent water clocks being constructed in temples and observatories long after mechanical clocks had become available. Even today, some traditional temples maintain the use of water timekeeping for certain rituals, preserving a technological tradition that connects modern worshippers to ancient practices and philosophical understandings of time's fundamental nature. Meanwhile, as incense clocks marked the hours with fragrant smoke in Chinese temples and water clocks measured sacred intervals in Indian courtyards, a horological revolution of an entirely different nature was gathering momentum in medieval Europe, one that would eventually transform humanity's relationship with time itself. The development of mechanical clocks using weight-driven mechanisms and verge and foliot escapements represents one of the most significant technological breakthroughs in history, moving timekeeping from the realm of natural phenomena like flowing water or burning incense into the precisely engineered world of gears, weights, and regulated motion. This transition didn't just improve accuracy, it fundamentally changed how people perceived time, transforming it from something observed in nature to something manufactured by human ingenuity. The heart of this revolution was the verge escapement, a deceptively simple yet profoundly important mechanism that allowed for the controlled release of energy from falling weights. Picture a vertical rod with two pallets that engage with a crown wheel, allowing it to escape tooth by tooth in a rhythmic back and forth motion. This escapement, coupled with the foliot, a horizontal bar with adjustable weights that oscillated to regulate the speed, created the first truly mechanical timekeeping system that could operate independently of environmental conditions. The distinctive tick-tock sound that would become synonymous with clocks was born from this ingenious invention, representing the audible heartbeat of a new era of time measurement. What made this system revolutionary was its ability to translate the continuous force of gravity into discrete, measurable increments of time, creating a reliable pacemaker that could govern the movement of clock hands with unprecedented consistency. These early mechanical clocks began appearing in European church towers and municipal buildings during the 13th century, and their impact on medieval society was nothing short of transformative. The massive public clocks installed in places like Wells Cathedral in England or the Palazzo Vecchio in Italy didn't just tell time, they organized entire communities around a shared temporal framework. Their ringing bells marked the hours for market operations, court sessions, and civic events, creating a rhythm of urban life that was both audible and visible to all citizens. The very word clock derives from the Latin clocca, meaning bell, highlighting how these devices announced time as much as displayed it. This public timekeeping created a new form of social synchronization that would eventually lead to the regimented time consciousness characteristic of modern societies. The technological evolution of these mechanical marvels accelerated rapidly throughout the 14th and 15th centuries. Clockmakers began adding multiple hands to show hours, minutes, and sometimes even seconds, though the latter required precision that would remain elusive for centuries. Astronomical displays became increasingly sophisticated, with dials showing the phases of the moon, the position of the sun in the zodiac, and the movement of planets according to the Ptolemaic system. Automated figures known as jacquemarts would strike bells on the hour, while elaborate astronomical theaters might feature moving representations of the Virgin Mary, rotating stars, or processions of apostles. The clock in Prague's Old Town Square, with its complex astronomical dial and animated figures, remains perhaps the most famous example of this medieval horological artistry, but similar marvels appeared in cathedrals and town halls across Europe. A crucial breakthrough came with the invention of the mainspring in the early 15th century, which liberated clocks from their stationary positions and allowed for portable timekeeping. This coiled spring could store energy much like falling weights, but in a compact form that made personal timepieces possible. The first portable clocks, often called clock watches, appeared around 1500, though they remained expensive luxury items owned only by the wealthiest aristocrats. These early portable devices faced significant challenges with accuracy due to the variable force of the unwinding spring, a problem eventually solved with the invention of the stackfried, and later the fusee, conical devices that equalized the force as the spring unwound. This portable timekeeping technology would eventually evolve into pocket watches and eventually wristwatches, putting personal time measurement within reach of ordinary people centuries later. The single most important improvement to mechanical timekeeping arrived in the mid-17th century with Christian Huygens' invention of the pendulum clock in 1656. The pendulum's natural periodicity provided a far more reliable regulator than the foliate balance, reducing error from perhaps 15 minutes per day to less than 1 minute. Almost overnight, timekeeping accuracy improved by an order of magnitude, making mechanical clocks truly precise scientific instruments rather than just approximate timekeepers. The seconds pendulum, approximately 1 meter long with a period of exactly 2 seconds, became a new standard of precision that allowed for the division of time into seconds with reasonable accuracy. This breakthrough coincided with the needs of emerging scientific revolution, providing the precise time measurement required for experiments in physics, astronomy, and navigation. The social and cultural impact of these mechanical timekeepers extended far beyond their practical functions. They embodied the medieval worldview that saw the universe as a great clockwork mechanism created by a divine clockmaker, a concept that would profoundly influence scientific thinking during the Renaissance and Enlightenment. The regularity and predictability of clock time helped foster a new conception of time as linear, measurable, and divisible rather than cyclical and event-based. This transformation paved the way for modern capitalism with its emphasis on productivity, schedules, and time management. The mechanical clock became both a symbol of and catalyst for the increasingly time-disciplined society that would characterize the modern Western world. These horological achievements also drove advances in precision engineering that would have far-reaching consequences beyond timekeeping. The gear-cutting techniques developed for clocks required new levels of precision in metalworking, while the need for accurate time measurement spurred improvements in mathematics, astronomy, and physics. The skills developed in clockmaking workshops would eventually contribute to the development of other precision instruments like telescopes, microscopes, and navigational devices. In many ways, the mechanical clock served as the foundational technology that made possible the scientific revolution and the industrial age that followed, proving that the measurement of time is not just a practical concern but a fundamental enabling technology for human progress. While European mechanical clocks were introducing the tick-tock regimentation of time to medieval town squares across the Atlantic Ocean, the Maya and Aztec civilizations were approaching timekeeping from a completely different philosophical foundation, one that saw time not as a linear progression to be measured, but as a sacred, cyclical force to be understood and harmonized with. Their calendar systems represent perhaps the most sophisticated integration of mathematics, astronomy, and theology ever achieved in the ancient world, creating what amounted to interlocking gears of time that synchronized human activity with cosmic patterns across multiple simultaneous cycles. Where European timekeeping sought to impose human order on the flow of hours, Mesoamerican systems sought to align human existence with the deeper rhythms of the universe itself. At the heart of this system was the remarkable 260-day sacred calendar known as the Tzolk'in, which intermeshed with a 365-day solar calendar called the Hob to create a 52-year calendar round that formed the basis of Mesoamerican timekeeping. The Tzolk'in wasn't derived from any obvious astronomical cycle like lunar months or solar years, but rather from the human gestation period and agricultural cycles deeply embedded in Mesoamerican culture. This calendar consisted of 20 day names combined with 13 numbers, creating 260 unique combinations before the cycle repeated. Each day carried specific spiritual significance and was believed to influence human affairs, making the calendar essential for determining auspicious times for everything from planting crops to conducting warfare, from naming children to crowning kings. The mathematical elegance of this system allowed priests to predict the qualities of future days with the certainty of astronomical events, creating a divinatory tool of immense social and political power. The 365-day solar calendar demonstrated equally sophisticated astronomical understanding, divided into 18 months of 20 days, each plus a special 5-day period considered highly dangerous and unlucky. What's particularly impressive is how the Maya compensated for the actual solar year length of approximately 365.2422 days, a calculation more accurate than the Julian calendar used in Europe at the same time. While we have no evidence they used leap years like the later Gregorian system, Maya astronomers were certainly aware of the discrepancy and made adjustments in their long-term calculations. This solar calendar governed agricultural activities, seasonal ceremonies, and civil administration, creating a practical framework for societal organization while maintaining sacred connections to the solar cycle and its associated deities. The true masterpiece of Mesoamerican timekeeping was the long count system, which provided a linear framework for tracking time across millennia with mathematical precision that still astonishes astronomers today. Unlike the cyclical calendar round that repeated every 52 years, the long count measured time from a fixed starting point. Most scholars believe August 11, 3114 BC in our Gregorian system, using a modified base 20 numbering system that included a place value for 360 days to accommodate the solar year. This allowed them to record historical events with absolute dating and make astronomical predictions across vast time spans. The famous completion of the 13th Bacton cycle in 2012, which sparked so much popular fascination, was just one example of how this system could mark significant chronological milestones across centuries of calculation. The astronomical knowledge embedded in these calendar systems reveals observation skills and mathematical capabilities that rivaled anything in the Old World. Maya astronomers calculated the Venus cycle at 584 days, incredibly close to the actual 583.92 days, and used this knowledge to coordinate military campaigns and royal successions, believing the morning star influenced human affairs. Their eclipse predictions employed the Saros cycle, a period of approximately 18 years between similar eclipses, but refined with correction factors that improved accuracy beyond what Babylonian astronomers achieved. The Dresden Codex, one of the few surviving Maya books, contains detailed Venus tables and eclipse warnings that demonstrate sophisticated pattern recognition across generations of observation, all calculated without telescopes or other optical instruments. The Aztec calendar stone, often called the Sun Stone, represents the physical embodiment of this complex temporal philosophy, carved into 12 feet of solid basalt. Often mistakenly called a calendar, this magnificent artifact is actually a sophisticated cosmogram that integrates multiple time cycles with Aztec cosmology. At its center appears the face of the sun god Tanatea, surrounded by 4 square panels representing the previous eras of creation and destruction that the Aztecs believed had preceded the current world. Around this central motif, the 20-day signs of the sacred calendar form an inner ring, while 8 radiating arrows indicate the cardinal and intercardinal directions that structured Aztec spatial and temporal understanding. The entire composition encodes the Aztec belief that the current world would eventually be destroyed like its predecessors, and that human sacrifice was necessary to nourish the sun and maintain the cosmic order. The mathematical sophistication underlying these systems was extraordinary. Maya mathematicians had developed the concept of 0 centuries before it appeared in Europe, using a shell symbol that allowed for place value notation and complex calculations. Their vigesimal system, based on 20 rather than 10, was particularly well suited to astronomical computations involving multiple cycles of different lengths. They could calculate the time between celestial events with precision we would now express using fractions, but which they represented through elegant whole number ratios that maintained accuracy across long periods. This mathematical capability allowed them to create correction tables that accounted for the slight discrepancies between calendar time and actual celestial motion, keeping their systems aligned with observable reality across generations. The social and political function of these calendar systems extended far beyond timekeeping into the very fabric of Mesoamerican civilization. The ability to predict celestial events and determine auspicious days gave priestly classes enormous influence over rulers and common people alike. Kings would time their coronations, military campaigns, and monument constructions according to calendar cycles believed to ensure success and divine favor. The completion of calendar cycles often prompted major architectural projects, with new temples and pyramids being commissioned to mark significant temporal milestones. This integration of timekeeping with political power created a society deeply attuned to cosmic rhythms, where the measurement of time was inseparable from the exercise of authority and the maintenance of social order. What makes these achievements particularly remarkable is that they were accomplished without many technologies available to Old World civilizations. The Maya and Aztecs had no metal tools beyond relatively soft copper and gold, no wheeled vehicles for transportation or construction, and no draft animals to assist with heavy labor. Their astronomical observations were made with the naked eye, using crossed sticks or notched bones as sighting instruments rather than the brass quadrants and astrolabes developing in Europe and the Islamic world. Their mathematical calculations were performed using counting boards with maize kernels or cocoa beans rather than abacuses or written numerals. Despite these technological limitations, they achieved a level of calendrical sophistication and astronomical accuracy that remained unmatched in Europe until the Renaissance, demonstrating that intellectual achievement can flourish along different technological paths. The legacy of these Mesoamerican calendar systems continues to influence contemporary culture in surprising ways. The 2012 phenomenon, though based on misunderstandings of Maya cosmology, sparked global interest in their timekeeping achievements. Modern Maya communities still maintain aspects of the traditional calendar system for agricultural planning and religious ceremonies, preserving knowledge that has survived centuries of cultural disruption. Scholars continue to debate and discover new aspects of these complex systems, with recent research suggesting even more sophisticated astronomical correlations than previously recognized. These calendars stand as enduring testimony to human ingenuity in the face of fundamental questions about time, existence, and our place in the cosmos, questions that every civilization must answer in its own way, using the tools and concepts available to it. Yet, even as these magnificent Mesoamerican calendar systems tracked cosmic cycles across millennia with stone and mathematics, a different kind of timekeeping revolution was brewing in Europe, one born not from celestial observation but from desperate necessity and the relentless power of the ocean itself. The problem of longitude had plagued sailors for centuries, representing perhaps the most dangerous and expensive scientific challenge of the age. Without knowing their east-west position, ships frequently missed their destinations, ran aground on unexpected shores, or simply vanished into the vastness of the Atlantic, taking their crews and valuable cargoes to the bottom. The situation had become so dire that in 1714, the British government established the Longitude Act, offering a prize equivalent to millions of today's dollars to anyone who could solve this seemingly intractable problem. The quest would ultimately produce one of the most significant horological breakthroughs in human history, the marine chronometer. At the heart of this challenge lay a deceptively simple principle that had been understood for centuries but never successfully implemented at sea. Since the Earth rotates 360 degrees every 24 hours, each hour of time difference between a ship's local noon and a fixed reference point translates to 15 degrees of longitude. The solution seemed straightforward: carry an accurate timepiece set to the time at your home port, compare it to local solar time aboard ship, and calculate your position. The reality proved infinitely more difficult, as the rocking motion of waves, extreme temperature variations, changes in humidity, and the constant force of gravity working on delicate mechanisms made accurate timekeeping aboard ships seemingly impossible. Pendulum clocks, the most accurate timekeepers on land, were completely useless on a rolling vessel, leaving sailors to rely on dead reckoning and celestial navigation methods that could leave them hundreds of miles off course after weeks at sea. The man who would ultimately solve this problem wasn't a renowned academic or established clockmaker, but a self-educated carpenter and mechanic from Yorkshire named John Harrison. His approach was revolutionary from the start. Rather than adapting existing clock designs, he reimagined timekeeping from first principles, creating increasingly sophisticated marine timekeepers that defied conventional wisdom. His first marine clock, known as H1, completed in 1735, already showed remarkable innovation with its paired balances connected by springs that counteracted the ship's motion, maintaining timing consistency even as the vessel pitched and rolled. Though it performed well in sea trials, Harrison knew he could do better, spending the next 3 decades refining his designs through H2 and H3, each incorporating new solutions to the problems of marine timekeeping. Harrison's masterpiece, the H4, completed in 1759, represented such a radical departure from his previous work that it barely resembled a clock at all. Rather than the massive counterbalanced machines he had previously built, the H4 looked like an oversized pocket watch, about 5 inches in diameter and weighing 3 pounds. Within this compact case lay innovations that would influence precision timekeeping for centuries to come. The device featured a revolutionary escapement that required no lubrication, a crucial improvement since oil viscosity changes with temperature could affect accuracy. It incorporated a bimetallic strip that automatically compensated for temperature changes by adjusting the balance spring's effective length, maintaining consistent timekeeping from tropical heat to Arctic cold. The balance wheel itself was a masterpiece of precision engineering, beating 5 times per second, far faster than contemporary watches, which helped average out errors caused by the ship's motion. The true test came during a voyage to Jamaica in 1761, when the H4 performed with accuracy that seemed almost magical. After 47 days at sea, the timepiece had lost just under 5 seconds, an error of only 1¼ minutes of longitude, far better than the requirements set by the Longitude Act. Even more remarkably, on the return voyage, the H4 actually corrected the ship's estimated position by nearly 100 miles, preventing what could have been a disastrous navigational error. Subsequent tests confirmed this wasn't luck but reproducible precision, with the timekeeper maintaining accuracy within seconds per day despite the challenging marine environment. Harrison had finally solved the longitude problem that had stumped the greatest scientific minds of his era, though bureaucratic delays and political maneuvering would prevent him from receiving full recognition and compensation for his achievement until the very end of his life. The impact of Harrison's breakthrough extended far beyond the recognition of one brilliant inventor. His innovations established the fundamental principles that would govern precision timekeeping for the next 2 centuries, influencing everything from pocket watches to eventually wrist chronometers. The temperature compensation techniques, anti-friction devices, and high-frequency balances he pioneered became standard features in quality timepieces. Perhaps most importantly, he demonstrated that extreme precision was achievable even under the most challenging conditions, inspiring generations of horologists to push the boundaries of what was possible in mechanical timekeeping. The marine chronometer's effect on global navigation was nothing short of transformative. Suddenly, ships could determine their position with unprecedented accuracy, making transoceanic travel vastly safer and more predictable. This precision navigation enabled the detailed mapping of coastlines, the accurate charting of ocean currents, and the establishment of reliable trade routes that connected the world as never before. The age of exploration accelerated dramatically as navigators could now venture into unknown waters with confidence they could return safely. Commercial shipping benefited enormously too, with reduced voyage times, lower insurance costs, and fewer losses of ships and cargoes. The chronometer quite literally made the global economy possible, enabling the regular, scheduled transportation of goods and people across oceans with a reliability that had previously been unimaginable. What makes Harrison's achievement particularly remarkable is how it built upon the ancient principles we've explored throughout our journey, while representing such a dramatic leap forward. The temperature compensation in his chronometer echoed the understanding of thermal effects that Persian water clock engineers had mastered centuries earlier. His precision, bearings, and friction reduction techniques refined concepts that had been developing in European clock towers and monastic timekeepers. Even his approach to solving a practical problem through mechanical innovation followed in the tradition of Su Song's clock tower and the sophisticated water distribution timers of ancient Persia. Harrison stood on the shoulders of giants, but he saw farther than any who came before him, creating an instrument that would enable humanity to finally conquer the last great uncertainty of ocean navigation and truly connect the world through precise time measurement. While the marine chronometer represented the pinnacle of portable precision timekeeping, reaching across oceans to connect continents, The ancient Greeks had already perfected a different kind of public timekeeping device that connected entire communities to the rhythms of the cosmos right in their town squares. The parapegma stands as a fascinating example of how Greek civilization transformed complex astronomical knowledge into accessible public information, creating what might be considered the ancient world's most user-friendly interface for understanding time, weather, and the seasons. Unlike the intricate geared mechanisms of the Antikythera device or the monumental scale of water clocks, the parapegma achieved its sophistication through elegant simplicity, a series of holes and pegs that made celestial cycles tangible and manageable for everyday citizens. Imagine walking through the agora of ancient Athens and encountering a stone slab about the size of a modern bulletin board, its surface carefully inscribed with columns of dates and corresponding astronomical information. This was the parapegma, a public calendar that tracked the relationship between celestial events and seasonal changes with remarkable precision. Each day, a designated official would move a peg to the next hole, marking the passage of time while simultaneously indicating which stars would be rising or setting, what weather patterns might be expected, and which agricultural activities should be undertaken. This simple mechanical action connected the community to cosmic patterns that governed everything from sailing schedules to planting times, making sophisticated astronomical knowledge available to farmers, merchants, and travelers who might never study formal astronomy. The true genius of these devices lay in their synthesis of centuries of observational data into practical, actionable information. Many parapegmata included detailed inscriptions based on the work of famous astronomers like Eudoxus, Meton, and Callippus, who had spent lifetimes recording the relationships between celestial events and terrestrial phenomena. The rising of the star Sirius might be associated with the onset of hot summer weather, while the appearance of the Pleiades in the morning sky could signal the beginning of the sailing season or the time to plant certain crops. These correlations weren't merely superstitious folklore but represented careful empirical observation across generations, creating a reliable database of seasonal knowledge that helped Greek society optimize agricultural production, maritime trade, and resource management. What made the parapegma particularly innovative was its modular design that could be updated as astronomical knowledge improved. Unlike fixed calendars carved in stone, the peg and hole system allowed communities to adjust their understanding of celestial cycles as more accurate observations became available. When Meton discovered the 19-year cycle that better synchronizes lunar and solar calendars, cities could update their parapegmata without having to create entirely new monuments. This adaptability made the parapegma a living document rather than a fixed inscription, reflecting the Greek commitment to revising knowledge based on new evidence and improved understanding, a remarkably scientific approach for the ancient world. The educational function of these public calendars cannot be overstated. In a society where formal education was limited to a privileged few, the parapegma served as an open-air classroom where ordinary citizens could learn about astronomy, meteorology, and the natural world simply by observing the daily peg movements and reading the associated inscriptions. The device often featured multiple columns of information, one tracking the sun's progress through the zodiac, another noting significant star phases, and additional columns providing weather expectations and agricultural advice. This multidimensional approach helped citizens develop a holistic understanding of how celestial patterns influenced their daily lives and economic activities, creating a population that was remarkably astronomically literate by ancient standards. The parapegma's design also reflected the Greek philosophical concept of cosmos, the idea that the universe operates according to orderly, understandable principles that can be discerned through observation and reason. By making these cosmic patterns visible and predictable, the parapegma reinforced the Greek worldview that humanity could comprehend and work within natural laws rather than being subject to capricious divine intervention. This confidence in human reason and empirical observation would eventually become one of Greece's most important contributions to Western thought, helping to lay the foundation for the scientific revolution that would occur centuries later. Surviving examples and descriptions of parapegmata show remarkable consistency across the Greek world, suggesting a shared scientific culture that connected distant colonies to the intellectual centers of Athens and Alexandria. A merchant traveling from Massalia, modern Marseille, to Ephesus would find similar astronomical information displayed in public spaces, using familiar terminology and reference points. This standardization facilitated trade, communication, and cultural exchange across the Mediterranean, creating a common temporal framework that helped bind the far-flung Greek world together despite political divisions and geographical separation. The legacy of the parapegma extends far beyond the ancient world in ways we might not immediately recognize. The concept of a public calendar displaying astronomical and seasonal information evolved into the medieval books of hours and modern almanacs that continue to provide similar guidance to farmers, gardeners, and outdoor enthusiasts. The idea of correlating celestial events with weather patterns persists in traditional knowledge systems around the world and is even finding new relevance as scientists study the potential relationships between astronomical cycles and climate patterns. This humble device of holes and pegs represents one of the most enduring ideas in human history, that by carefully observing the heavens and recording our findings, we can better understand and navigate our world, finding patterns in the cosmos that help us organize our lives here on Earth. While European mechanical clocks were introducing their distinctive tick-tock rhythm to medieval town squares and monastic water clocks regulated prayer schedules with hydraulic precision, within the vibrant intellectual centers of the Islamic Golden Age, a different kind of horological marvel was emerging, one that transformed timekeeping into a multisensory spectacle of art, science, engineering. Islamic water clocks with automata represented perhaps the most complete integration of technological sophistication and artistic expression in the history of time measurement, creating devices that didn't just tell time but performed it through moving figures, musical elements, and visual drama that captivated observers while maintaining remarkable accuracy. These magnificent creations stood at the intersection of practical timekeeping, mechanical innovation, and cultural demonstration, showcasing the advanced scientific capabilities of Islamic civilization during its golden age. The undisputed masterpiece of this tradition was the elephant clock, designed by the brilliant engineer Ismail al-Jazari in the early 13th century. This extraordinary device wasn't merely a timekeeper but a complete mechanical theater that brought the principles of hydraulics and automation to life in breathtaking fashion. Picture a life-sized mechanical elephant carrying an elaborate howdah on its back, with a turbaned figure sitting atop it and various mythological creatures arranged around the structure. Every hour, this complex assembly would spring into action. Serpents would sway, birds would chirp, the turbaned figure would raise its arms, and a ball would drop from one creature to another, all powered by nothing but carefully regulated water flow. The entire performance culminated in the striking of a cymbal or the sounding of a trumpet to mark the completion of another hour, creating a public spectacle that both educated and entertained while faithfully tracking the passage of time. What made these devices truly revolutionary was their sophisticated use of water control mechanisms that maintained consistent timekeeping accuracy despite the varying pressure heads in their reservoirs. Islamic engineers developed constant flow systems using multiple chambers and overflow mechanisms that ensured water entered the timing mechanism at a steady rate regardless of how much water remained in the main tank. Some clocks incorporated mercury instead of water in their regulators, the dense liquid being less affected by temperature changes that could alter water's viscosity and thus its flow rate. The most advanced designs featured float mechanisms connected to gear trains that translated the steady rise or fall of water levels into the complex motions of automated figures, musical elements, and time indicators. This hydraulic precision allowed these clocks to maintain accuracy within minutes per day, rivaling the best mechanical timekeepers of their era while operating on completely different principles. The cultural significance of these automata-filled timepieces extended far beyond their practical timekeeping function. They served as physical demonstrations of Islamic engineering prowess and scientific achievement, often commissioned by rulers to impress visitors and reinforce their reputation as patrons of knowledge and innovation. The elaborate designs frequently incorporated elements from multiple cultures, the elephant representing Indian influence, phoenixes and dragons showing Chinese inspiration, and Arabic script and architectural elements reflecting Islamic identity, creating a visual language of multicultural exchange that characterized the Islamic Golden Age. These clocks weren't hidden away in private collections but displayed in public spaces where they could be admired by scholars, merchants, and ordinary citizens alike, serving as both scientific instruments and public monuments to human ingenuity. The mechanical sophistication behind these water clocks represented significant advancements in multiple engineering disciplines. The gear systems used to translate water power into complex motions showed understanding of mechanical advantage and torque transmission that wouldn't be matched in Europe for centuries. The automated figures incorporated cams, levers, and linkages that could produce surprisingly lifelike movements from simple hydraulic power. Musical elements were triggered by carefully timed releases of water or weights that would strike bells, blow air through pipes, or pluck strings to create auditory time signals. Some clocks even featured what we might now call early programming sequences of actions that would occur in specific orders, with different automata activating at different times to create narrative performances that unfolded throughout the day or week. The educational value of these elaborate timekeepers cannot be overstated. They served as physical textbooks demonstrating principles of hydraulics, mechanics, and astronomy to students in madrasas and to the broader public. The visible operation of water wheels, gears, and float mechanisms made abstract engineering concepts tangible and understandable. Astronomical elements often included in these clocks, such as models showing planetary movements or zodiac indicators, provided visual education about celestial mechanics. Even the cultural elements incorporated into the designs taught viewers about the diverse influences and connections within the Islamic world, making these clocks multidimensional educational tools that blended science, art, and cultural studies in a single magnificent package. What's particularly impressive about these Islamic water clocks is how they integrated multiple timekeeping traditions while adding unique innovations. They built upon earlier Greek and Roman water clock designs but incorporated geared mechanisms that showed influence from earlier Byzantine and possibly even Chinese horology. The use of mercury regulators reflected understanding of fluid dynamics that wouldn't be formally described in scientific terms for centuries. The automation elements showed similarities to earlier Hellenistic devices, but achieved new levels of complexity and integration. This synthesis of knowledge from multiple cultures, combined with original Islamic innovations, created timekeeping devices that were both technically superior to anything previously created and artistically magnificent in ways that had never been attempted before. The legacy of these magnificent devices extends far beyond their historical period. The engineering principles developed for these water clocks influenced later mechanical clock design in both the Islamic world and Europe. The concept of using automata to mark the passage of time evolved into the jacquemarts of European cathedral clocks and the elaborate astronomical clocks of the Renaissance. The precise water control mechanisms contributed to advancements in irrigation technology and water management systems that improved agricultural efficiency across the Islamic world. Even the multidisciplinary approach these clocks represented, blending art, science, engineering, and education, serves as an early example of the integrated innovation that would characterize later technological revolutions. Perhaps most importantly, these Islamic water clocks with automata stand as powerful reminders that technological advancement can follow multiple paths. While Europe was developing weight-driven mechanical clocks, Islamic engineers were perfecting hydraulic timekeeping to levels of sophistication that wouldn't be matched elsewhere. Their achievements demonstrate that progress isn't always linear and that different cultures can arrive at similar technological capabilities through different approaches and principles. These magnificent creations represent a pinnacle of scientific and artistic achievement that emerged from a culture that valued both knowledge and beauty, that saw no contradiction between technological innovation and artistic expression, and that understood time itself as something to be measured with precision, understood with wisdom, and celebrated with creativity. Long before the first pyramids pierced the Egyptian horizon or the foundations of Mesopotamia's ziggurats were laid, our Neolithic ancestors were engaged in an engineering project of almost unimaginable ambition, transforming the very landscape itself into a massive astronomical computer. These weren't simple stone circles or random collections of monoliths. They were precisely calibrated instruments carved from living rock, designed to track the complex dance of celestial bodies with a sophistication that still leaves modern astronomers in awe. The world knows their names: Stonehenge on England's Salisbury Plain, Newgrange in Ireland's Boyne Valley, the endless rows of standing stones at Carnac in France, but we're only beginning to understand their true purpose as the most durable calendar systems ever created by human hands. Consider the sheer scale of the enterprise at Carnac, where over 3,000 massive stones stretch across the Breton landscape in parallel rows extending for nearly 4 miles. The alignment isn't random. The stones are positioned with such geometric precision that they form a gigantic astronomical observatory, with specific stones marking the rising and setting points of the sun and moon at key times throughout the year. During the winter solstice, from certain vantage points along the rows, the sun appears to roll along the horizon from one strategically placed menhir to another, creating a celestial spectacle that would have told ancient observers exactly when the shortest day had arrived and the sun's return was imminent. This wasn't just art or ritual, it was practical astronomy on a monumental scale, engineered to provide reliable seasonal markers for agricultural planning and social organization. The technical achievement becomes even more impressive when we examine sites like Newgrange in Ireland's Boyne Valley. This massive circular mound, older than both Stonehenge and the Egyptian pyramids, features a precisely engineered roof box above its entrance that performs a specific astronomical function with breathtaking accuracy. For just 5 days around the winter solstice, as the sun climbs above the horizon, a narrow beam of sunlight enters through this specially designed opening and travels down a 60-foot passageway to illuminate the inner chamber's central spiral carvings. The alignment is so exact that even a slight miscalculation in the orientation of the passageway by as little as a single degree would mean the sunlight would miss its target completely. This required not only advanced understanding of solar movements, but sophisticated surveying skills to orient the massive structure with such precision, using nothing but simple tools and celestial observation. What's truly revolutionary about these Neolithic calendars is their ability to track not just annual solar events, but the more complex 18.6-year cycle of the moon. At Stonehenge, the arrangement of the sarsen stones creates alignments that capture the moon's extreme rising and setting positions during what astronomers call major and minor standstills, points in the lunar cycle that only occur every 18+ years. The station stones positioned around the periphery form a perfect rectangle whose sides align with these lunar extremes, while the famous heel stone marks the northernmost rising point of the moon during major standstill years. This means the builders weren't just tracking days or seasons, they were maintaining accurate records of celestial patterns across generations, preserving knowledge that required careful observation and recording over decades before it could be encoded into stone. The construction methods themselves boggle the modern mind when we consider the limitations these prehistoric engineers faced. The bluestones at Stonehenge were transported from the Preseli Hills in Wales, a distance of over 150 miles, using technology that remains mysterious to archaeologists. The larger sarsen stones, weighing up to 50 tons each, were moved from quarries 20 miles away and precisely shaped using only stone hammers and antler picks. At Newgrange, the massive curbstones that surround the mound were carved with intricate spiral patterns that may have functioned as astronomical notation, while the white quartz facade was imported from mountains over 50 miles distant. This represents not just technical skill but incredible social organization, the ability to coordinate hundreds of workers over generations to complete projects whose full purpose might not be realized within a single lifetime. The cultural significance of these calendar monuments reveals a Neolithic worldview where human society was deeply integrated with cosmic patterns. The alignment of these structures with solstices and equinoxes suggests these weren't merely practical agricultural calendars, but sacred spaces where the community could witness and participate in the fundamental rhythms of the universe. The illumination of Newgrange's chamber during winter solstice, the darkest time of year, would have been a powerful symbol of hope and renewal, reinforcing social cohesion during difficult seasonal transitions. At Stonehenge, the alignment of the avenue with the summer solstice sunrise suggests processional ways where communities could literally walk into the rising sun during ceremonial occasions, physically embodying their connection to celestial cycles. Perhaps most remarkably, these stone calendars continue to function with undiminished accuracy thousands of years after their creators vanished. The winter solstice sun still illuminates Newgrange's chamber. The moon still rises over Stonehenge's heel stone during major standstills, and the Karnak alignments still mark the sun's progression through the year. This endurance speaks to the sophistication of the original designs. These weren't devices that required recalibration or maintenance, but permanent fixtures aligned with celestial patterns that themselves remain constant over millennia. The stones stand as silent witnesses to a prehistoric scientific tradition that managed to encode complex astronomical knowledge into landscape features so durable they would outlast civilizations, languages, and even the memory of the people who built them. When we place these ancient marvels side by side with our modern atomic clocks and satellite-based timekeeping systems, what emerges isn't a story of primitive versus advanced, but rather a continuous thread of human ingenuity stretching across millennia. The fundamental drive remains identical: our species' relentless pursuit to measure, understand, and master time itself. What truly astonishes isn't how far we've come, but how incredibly close ancient engineers came to precision we associate exclusively with our digital age, using entirely different technological pathways. They achieved seconds per day accuracy with water pressure regulation and gear ratios where we use quantum vibrations of cesium atoms, yet both approaches satisfy the same human need for temporal order. Consider the underlying principles. Modern atomic clocks rely on the consistent vibration of atoms, a natural oscillator that's incredibly stable. Ancient timekeepers also looked to nature's consistent rhythms, using the reliable flow of water, the predictable movement of shadows, or the regular cycles of celestial bodies. The Mayan calendar's Venus calculations, accurate to within hours over 500 years, differ from our atomic precision only in degree, not in conceptual approach. Both systems observe natural phenomena and create measurement systems based on those observations. The real difference lies in our tools. Where they had stone, bronze, and water, we have quantum physics and satellite networks, but the intellectual leap of creating reliable measurement from natural consistency connects us directly to those ancient astronomers watching the same stars we see today. The social function of timekeeping reveals another fascinating parallel. Just as atomic clocks now synchronize global financial transactions, power grids, and internet communications, ancient devices like the Roman sundials or Chinese incense clocks coordinated markets, religious ceremonies, and agricultural activities across their respective empires. The scale has expanded from regional to global, but the purpose remains: creating synchronized human systems. The Tower of the Winds in Athens served as a public time utility, much like network time protocol servers do today, distributing accurate time to anyone who needed it. This democratization of precision, whether through shadow lengths on marble or microseconds through fiber optics, enables complex societal organization that would otherwise be impossible. Technological limitations forced ancient engineers to develop solutions that were often more elegant and durable than our modern equivalents. The Jantar Mantar sundials in India, still accurate after 3 centuries of exposure to the elements, represent a permanence that our digital infrastructure, with its planned obsolescence and constant updates, rarely achieves. Their water clocks with constant flow mechanisms maintained accuracy through principles of hydraulic engineering that we've only recently mathematically modeled with computational fluid dynamics. These ancient devices embodied sustainability constructed from locally available materials, requiring no external power source, and often continuing to function for centuries with minimal maintenance. In an age concerned with technological resilience, we might have something to learn from timekeeping systems that operated for generations without a single software update or replacement part. Perhaps the most profound connection lies in how both ancient and modern timekeeping reveal our place in the cosmos. GPS satellites must account for relativistic effects due to their orbital speed and Earth's gravity, a validation of Einstein's theories that would have delighted ancient astronomers who noticed similar subtle anomalies in planetary motions. The Antikythera Mechanism's correction for the Moon's irregular orbit using a pin and slot mechanism represents the same conceptual breakthrough as our relativistic corrections. Both recognize that the universe doesn't follow perfect circular motion and require sophisticated compensation. This continuous refinement process, where each generation builds upon previous observations to create more accurate models, represents the very essence of scientific progress across civilizations. The evolution of timekeeping also mirrors changes in how we perceive time itself. Ancient devices often emphasized cyclical time, seasonal patterns, planetary cycles, and repeating celestial events. Modern timekeeping has become increasingly linear and granular, focusing on ever smaller divisions of absolute time. Yet both approaches serve the same fundamental human needs: coordinating activities, understanding our environment, and finding meaning in temporal patterns. The atomic clocks that govern our digital world haven't replaced these ancient concerns. They've simply added another layer of precision to humanity's eternal conversation with time. a dialogue that began when the first astronomer noticed that shadows move in predictable ways and wondered what that pattern might reveal about the nature of existence itself. These 25 extraordinary timekeeping devices we've explored reveal a profound truth about human history that often gets buried beneath conventional narratives of progress. What we've discovered in forgotten ruins and ancient sites isn't merely a collection of curious artifacts, but compelling evidence that numerous civilizations achieved technological sophistication and scientific understanding that either matched or exceeded what would follow for centuries, in some cases not being surpassed until the modern era itself. This realization forces us to completely reconsider the timeline of human innovation and recognize that the path of progress is anything but linear. The intricate bronze gears of the Antikythera Mechanism, the precisely aligned stones of Mayan observatories, the hydraulic genius of Egyptian water clocks, and the massive stone instruments of Indian astronomy all speak to a level of engineering prowess and astronomical knowledge that we're only beginning to fully appreciate. What connects these diverse innovations across continents and millennia is humanity's enduring fascination with measuring time and deciphering cosmic patterns. This universal drive emerged independently in cultures separated by oceans, suggesting something fundamental about human consciousness. Our species seems hardwired to seek order in the cosmos and quantify our experience of existence. The Maya tracking Venus cycles with mathematical precision, the Babylonians compiling centuries of astronomical data on clay tablets, the Polynesians navigating vast oceans using mental star maps, and the builders of Stonehenge encoding lunar cycles into massive stones all represent different expressions of this same profound human impulse. Each approach reflects unique cultural perspectives and environmental adaptations, yet all share the common goal of understanding time's passage and our place within the cosmic order. Every one of these discoveries challenges our deepest assumptions about technological progress and the supposed superiority of modern civilization. The Antikythera Mechanism alone should shatter any remaining notions that ancient technology was primitive or unsophisticated. This device, with its differential gears and intricate mechanisms, demonstrates conceptual thinking and mechanical engineering that wouldn't be matched for over 1,000 years after its creation. Similarly, the precision of Mayan astronomical calculations, the hydraulic regulation in Persian water timers, and the architectural alignments of Neolithic calendar monuments all reveal capabilities that force us to reconsider what ancient peoples could achieve with the materials and knowledge available to them. These aren't anomalies, but rather evidence of technological traditions that were likely more widespread than we currently understand. Perhaps the most humbling lesson from these ancient marvels is how easily knowledge can be lost and must be rediscovered across centuries. The technological principles behind the Antikythera Mechanism disappeared from the historical record for over a millennium. The sophisticated astronomical understanding encoded in Mayan calendars was largely forgotten after the Spanish conquest. The engineering knowledge behind precise water clocks and mechanical automata was preserved in some cultures while being lost in others. This pattern of loss and rediscovery reminds us that technological advancement isn't guaranteed, or irreversible civilizations can and do forget, and progress can be interrupted for centuries before being regained. This historical reality should make us thoughtful about preserving our own scientific and technological knowledge for future generations. As we continue to uncover ancient marvels using increasingly sophisticated archaeological tools and technologies, we're gaining not only fascinating insight into past achievements, but also genuine inspiration for future innovation. The study of ancient timekeeping devices has influenced modern engineering in surprising ways. The mechanical principles behind some ancient devices, have inspired new approaches to precision instrumentation, while the materials science behind durable bronze gears and stone constructions has informed modern preservation techniques. More importantly, these discoveries inspire us conceptually, reminding us that human ingenuity can achieve remarkable things even with limited technological means, and that sometimes the most elegant solutions come from working with natural principles rather than against them. The precise measurement of time remains one of humanity's greatest and most enduring intellectual pursuits, connecting us across millennia through shared curiosity and ingenuity. From the water clocks of ancient Egypt to the atomic clocks of today, we've been engaged in a continuous conversation with time itself, seeking to understand its nature and measure its passage with ever-increasing accuracy. This journey has taken us from tracking shadows on stone to measuring quantum vibrations in cesium atoms, yet the fundamental impulse remains unchanged. The ancient timekeepers we've explored weren't just creating practical tools, they were attempting to comprehend the universe's deepest rhythms and humanity's place within the cosmic order. Their legacy reminds us that the quest for knowledge transcends cultural boundaries and historical periods, uniting us in a shared human endeavor to understand the mysteries of time and existence.